good. All right, we are here for the final stretch of HPG paper sessions. We got our 7th session, which is going to be on graphics applications. And our first presentation is going to be on real-time decompression and rasterization of massive point clouds from Raoul Gohl, Markus Schütz, Bernhard Kerbel, and PJ Naranjanan. So go ahead.
Thank you so much. So this is some great work by the student Raoul Gohl from IIIT Hyderabad. And unfortunately, he couldn't make it today because of some travel issues. So I'll be doing my best to present in his stead the material that he has prepared for us today. So the topic of real-time decompression and rasterization of massive point clouds, he actually had quite a few challenges there to overcome. So this is a quick overview of the individual problems and actually the sections that we want to give some attention in this presentation. So first of all, I'm going to talk about why we would even want to have such large point cloud datasets and what the challenges are there. And then we're going to look at some previous work, followed by our pipeline and our methods for compressing, and then lastly look in what we can achieve with them in real-time rendering. Okay, so first of all, for the motivation, we all know about LiDAR scanning, and LiDAR scanning can create some very beautiful landscapes and imagery and 3D datasets for us. But it tends to generate millions and billions due to the sheer scale, for instance, or the sampling precision, or the frequency of the scan being used. And the videos that we have here demonstrate the renderings of various interesting real-world datasets, and the largest of which has over 6 billion points in it. And we have some nice solutions for handling such massive point clouds in real time, as I'll show in a second, but in their raw form, these datasets require up to 90 gigabytes of storage, which even a modern-day beefy GPU cannot handle. So, looking into our, let's say, state-of-the-art real-time rendering solutions for massive point clouds, Schütz and colleagues have previously shown the benefits of using software rasterization for rendering large point clouds. And they have a 1 point per pixel rendering approach that can visualize the equivalent of 2 billion points per second at the speed of 60 FPS on modern GPU hardware. Now I say equivalent because unfortunately they cannot achieve this in practice because 2 billion points or more simply cannot be stored on a commodity GPU. And in our work, we use the flexibility of software rasterization to basically tackle this problem and see how much farther can we go, and can we actually put these massive real-world datasets on commodity hardware for real-time rendering. Now, our renderer uses the basic 1 point per pixel solution that the authors came up with, and that's using compute shaders. So as a quick recap of their work, there are usually batches of points, and they get scheduled onto thread blocks on the GPU. And each thread in the thread block then simply projects points to screen space, and the IDs of the closest points are tracked using atomic minimum operations, which are very, very fast in recent hardware generations. And then in the second pass, the stored IDs of the closest points are substituted with RGB to obtain the final image. And this can be combined with other methods, for instance, with multi-sampling. So multiple closest points are being taken together, blended together to give you a high-quality shading solution that is similar to anti-aliasing. Now that we've talked about the basic setup, let's look at some cues on how we could compress the point cloud data that we're dealing with. So LiDAR scanners often have fixed sampling rates, which result in points lying at certain intervals. And for instance, LS-ZIP is famous for compressing and being a very valuable tool for leveraging these cues to compress scans by up to 7x. So very commonly used in industry, very popular solution. However, this is purely out of core. This is usually something that exclusively happens offline, both for compression and decompression, and to enabling and optimizing the storage on disk rather than at runtime. So we attempt to tackle this task with similar solutions and similar queues, but decompressing these large data sets actually on the fly while they're being rendered. So this is a challenging task. So let's see how we can use these queues that LS-ZIP builds on and then extend them and make them amenable to real-time processing. So we first realized that if we perform delta encoding on the coordinates first it induces a lot of repetition in the values, and we can significantly reduce overall entropy, which then facilitates post-working compression methods. So on the right-hand side, we see the f of the unique point coordinates values and how often they occur in a given regular data set. So here we have the x, y, z coordinates and the integer values that are usually stored in LAS. We can basically find how often each of these integer values appears and then basically plot their CDF, which is what we see on the right-hand side. Now if we switch to delta encoding, however, this distribution becomes very much skewed towards very few values that make up to 98% of the entire data. So basically going through the data set, figuring out the deltas and having them being represented rather than the actual absolute values makes the distribution much more skewed and significantly reduces the entropy. Now, an example of this concept. Let's take, for instance, the first 10 million points of this Morrow Bayesian shown here. And after evaluating the deltas, we find that only the top 128 values are enough to represent 85% of the points in it. Now with the lower entropy, we can select these most occurring delta values and represent them using, for instance, only a few bits with Huffman encoding, which is lossless in nature, so we can actually recreate the points to their full precision afterwards. And this is important, for instance, in close-up views for multi-scale data, or for common practical use cases for point cloud data like surveying or distance measuring. So you have that data on GPU, on chip, and you're not losing the precision. It's still in there if you wanted to retrieve it. So our compression steps go like this. Firstly, we sort the points in Morton order to induce some 3D spatial locality. And the points are then split into regular-sized batches of 64K points. And each batch is then independently compressed by using the delta encoding followed by Huffman encoding. Now the diagram on the right depicts how we compress a batch of points. So firstly, we find the deltas of the coordinates. We evaluate the frequency of the deltas and Huffman encode the most occurring values, and the ones that are not that frequent are stored separately in another buffer. And this will become clearer soon. So let me now talk a little bit about the clipped Huffman methodology. So traditionally, Huffman decoding requires a traversal from the root of the Huffman tree to its leaves for each individual code word that you are analyzing or decompressing. But not only is this an expensive operation, but it is also not very SIMD friendly, which is the architecture that we are operating on the GPU. So to counter this, we construct our clipped Huffman method, which is suitable to run on the GPU actually, building and influenced by the work of Weisenberger and Schmidt from 2018. So there's some involvement section ahead, which some diagrams. So hope you are already awake. So let's take a toy example of 9 symbols, namely letters A to I, with the probability distribution as shown on the right-hand side. And we can construct a Huffman tree out of this distribution quite easily following conventional approaches, as shown on the left-hand side, where all the symbols are at leaf nodes. And here, D and I, if you pay attention, make up for 88% of the total distribution. Now, we choose a maximum code word length L, in this case 3, and then clip the Huffman tree by cutting it after the level L. So now all the nodes beyond level L are simply discarded, and the symbols beyond this level will not be Huffman encoded, and instead those will be separately stored. So those actual symbols are going to a separate buffer. And now all leaf nodes that don't lie at L are projected to level L exactly. So leaf nodes that have a level lower than L are extended down and create multiple dummy nodes at that level L, and they are D and I here. The leaf nodes that have a level higher than L are backtracked up to create collision nodes, is what we call them, at level L. And they are in this case B, C, F, G, and H. Now after the projection, all the nodes at level L are used to create a lookup table of size 2 to the power of L. And the table has 2 columns, one for the symbol and one for the length of the actual code word. The code word is the index itself. So let's fill this table up. So let's, for instance, start with the code word 000 that maps to the symbol A and has a length of 3. Now, the code word 001 maps to a collision node in our case. So we set the code word length as negative while still preserving the length of the code word. And the negative bit basically indicates that this is a collision node. So something that will have to be looked up in a separate buffer. And the code word 010 and 011, both of them map to the same symbol, so both dummy nodes have a length of D and have the same symbol stored. Now, similarly, we can fill the rest of the table in the same procedure. So that's the position basically for filling up this entire table. Now let's try to encode the symbols of a sequence I, B, and A. So I maps to the code word 11. And then B is a discarded node, so we append the code for its collision node in our Clipped-Huffman tree, and that is 001. And we also add it to the second buffer directly, our separate buffer that we have. And A maps to 000 in this case, and with that we're basically done encoding the message, a total length of 8. Now let's decode it back. Now we know that the maximum code word length is L, which is 3 here. So we look up the first 3 values, or bits in this case, which decode to the symbol I and code word length 2. So we're looking at 110, which basically we find in our lookup table that is the entry for I, and we have the stored length of 2 there. Okay? So that basically gives us the first part of the message back. Now we realize that only 2 bits were used, because that's the second entry in the table. So we shift back by 1 and then restart basically the procedure again and keep decoding in this way. So then we have the new information, which is 001 in this case, and that's a negative entry. So that tells us that this is a collision node, and we actually need to look into the second buffer for the actual symbol. So this will be a more expensive lookup, but because these values are expected to be very rare, this is something that we basically do as contingency when the fast track directly decoding the symbols from the table doesn't work immediately. Okay, good. So, and finally, the last 3 bits are used to directly decode the symbol A. And with that, we have recovered the full message with this Clipped-Huffman tree. So, the 64K points that we have in the individual batches are divided into equally sized streams of data, and then they are decoded by each thread independently. So, all the threads in the thread block share the same Huffman backbone. So we clip the Huffman tree at the maximum level such that the decoder table actually can fit into GPU shared memory. We find that after clipping like this, we observe that around 98% of the deltas are able to be Huffman compressed, and only 2% of them need to be stored separately. So this results in a more than 4 times compression of the geometry, lossless. Sorry, I did not put up the text accordingly, but the message is basically the same. So, we have now described how a batch of points is encoded and decoded on the GPU, but unfortunately life isn't so simple, because since Huffman encoding uses variable-sized codes, we have to have some special treatment there, because these individually sized codes can lead to actually uncoalesced access patterns, and this is a little something for those of you who are interested in coalescing and uncoalescing and making GPU accesses efficient. So this uncoalesced behavior, or this different lengths of keywords, causes different Huffman encoded streams to have different lengths, even when they have to encode the same amount of symbols. And to understand this better, let's quickly take a toy example here with just 2 threads. And here, thread 0 contains code words that are twice as long as thread 1. So it needs to read twice as much memory over its entire procedure. So for instance, imagine every symbol that thread 0 is trying to decode is 8 bits, while every symbol that thread 1 is trying to decode is 4 bits. Let's say by coincidence in this case. Okay? And in this diagram, the lighter shaded colors indicate data to be read by thread 0, and darker shaded colors indicate data to be read by thread 1. So again here, different reference streams have different length. And let's for instance say in this case here, both of them, the two threads have to decode 6 words, with thread 0 having longer code words and thread 1 having shorter ones. So requiring fewer memory blocks to actually get all the data into the registers. Now for decoding code word 0, their respective code word 0, both the threads read from their respective memory block 0 as well. Okay? For decoding code word 1, thread 0 moves to a new memory block, while thread 1 does not go ahead. And this is because, as we said, thread 1 here has 2 code words stored in the same amount of memory as thread 0, because each of them is only half as long. Now, when decoding code word 2, thread 0 moves ahead, sorry, jumped ahead there. When decoding code word 2, thread 0 moves ahead again, and thread 1 moves ahead for the first time, since it has used all the code words in its previous block. And then finally, in this manner, both the threads keep traversing memory locations at different speeds until all 6 code words are successfully read and decoded. So in memory, the streams are stored in a flattened manner. And if we store them naively or even interleaved, the 2 threads read from memory locations that keep growing farther and farther apart. So over time, we're actually introducing very uncoalesced accesses like this. And this causes uncoalesced memory access, which is not GPU friendly, and the streams cannot be trivially stored in transposed memory or with some tricks, since they have different sizes. So to solve this problem, we propose to pre-compute the order in which the memory will be read at runtime and rearrange the memory in that order. Because we actually know the decompression procedure fully well, we can actually predict how threads will progress and then simply predict how memory will be accessed and then reorder these entries in such a way that they will be read quite optimally from memory with maximum coalescence. And this is done by assigning each memory block a 2-tuple key. Here int, where I is the first code word to occur in a memory block, and t is the thread index. And it just so turns out that upon sorting using these assigned keys, we obtain an order which ensures that threads always access memory locations close to each other. So for more details on why this is true, please refer to the paper, but in practice, the behavior would now look something like this, where when the first code word is read, thread 0 and thread 1 read data from nearby memory addresses, and this actually stays true as the procedure continues. So even though they have differently sized data to decode, over time they progress in the same manner and always at the same time simultaneously access close memory locations. And this has a significant impact on the cache hit rate of L1, basically raising it up in our practical cases from 10% to 70%. Now, let's talk a little bit about level of detail support. We have crafted an efficient decompression scheme for points, but of course it isn't free of cost. So we measure the raw processing power throughput after adding the decompression, and we observe a drop compared to state-of-the-art work. But we observe that our peak throughput is 124 million points per millisecond compared to 184 million points per millisecond. I actually believe that, oh no, sorry, that's true, yeah, millisecond, indicating that the trade-off isn't actually that bad. So why is it not actually faster? Because we are actually now doing less memory traffic. We are loading less data because it's compressed by 4 times. So why isn't that bottleneck that's usually the main culprit of poor performance simply removed? Why is it not faster? And the short answer in this case is bank conflicts. Because our decoder tables are stored in shared memory, and as we said before, values are frequent, or the values that we're interested are frequent, meaning also that collisions are pretty frequent. And this is bad news for shared memory because it doesn't really like those collisions to the same entries in the decoder table, and it will give you bank conflicts. We haven't yet found the perfect way to get rid of them or minimize them, so this is something that we will have to attack in future work. But if we look back to the work that we are building on, so Schütz and colleagues, they actually get part of their high performance from using a level of detail method. So we actually put our thinking caps and thought, okay, how can we come up with our own level of detail method, which is not that trivial because this LOD must basically be compatible with our differently sized data with our delta encodings. And if you take, for instance, the original LOD method of Schütz and colleagues, that doesn't out of the box work with delta encodings. So we basically had to come up with our own solution. So what we do is for every batch, we find the extent of its bounding box in screen space after projection and calculate its pixel coverage. And then depending upon the pixels touched, we render only a fraction of the points, decode and render only a fraction of the points using a linear drop-off as shown in the graph. So we still basically need to consume the data, but we no longer need to look it up from the decoder table. Now, this fraction here is min-capped at 10%, so at least 10% of every block that we are processing, of every batch that we are processing, will be processed and rendered. And this results in a quite relevant, efficient methodology, especially in faraway shots when millions of similar looking points can be projected to the same pixel. This LOD helps a lot in skipping over points which may not contributing to the pixel colors. And on this side here, we can see our level of detail visualization. On the very right-hand side, the batches close to the camera with a large pixel footprint are completely rendered, as indicated by the white shading, and batches that are far away of the scene are sparsely rendered, as indicated by the gray or darker shading. And in our paper, we quantified the errors in our images caused due to LOD and color compression. Here it is displayed using error maps. And please note that for better visualization here, the error has been multiplied by a factor of 10 to make it more obvious. So now for some results. We first checked the quality achieved with the pipeline. Our main competitor is the method that we are extending, that is the one by Schütz and colleagues from 2022. And we find that we can keep a high PSNR, which is maintained for large scenes we tested, indicating that we don't lose much due to the level of detail, or even with color compression to not only compress the position, but also the color information of the points, for which we can simply use BC1 encoding without a significant impact on quality or a consistent impact of quality, rather. And as you can see, the clipped Huffman approach can effectively compress billion of points. 98% of the points undergo encoding, and the compression ratio close to 4 times is always maintained in the data sets that we evaluated. We have tested our method against previous state-of-the-art on 2 GPUs. That was an RTX 3090 and an RTX 4060 laptop GPU. And in this table, we indicate those different models with their available memory in the different columns. So the 3090 has 24 gigabytes. That's the 24 gigabyte column for the 3090. And the 4060 has 8 gigabytes. And that column goes for that model. And in the paper, we look at different shading methodologies also, with basic being the closest point win scenario and the high quality shading, or HQS, which performs the anti-aliasing that I showed before. And for details, please kindly check the paper. And again, our main competitor here is the method by Schütz and colleagues from 2022. And from this first highlight, we can see we maintain competitive render times while consuming significantly less memory. And from the second highlight, you can see that we can render and maintain real-time rates on an 8 gigabyte laptop GPU for scenes which previous methods could not render on a 24 gigabyte GPU. So that's a huge enabler for people who are confronted with large-scale data sets. So in summary, with all these efforts, we now have a novel solution for visualizing extremely large data sets on less powerful machines in real time, preventing them from going out of memory with minimal sacrifices in quality and accuracy of rendering. And in short, our compression-based pipeline is fit for the demands of large-scale real-world data sets. It can handle large-scale data, it maintains high detail on demand, and allows for common use cases on data like inspection, surveying, or measuring, which was one of our key driving goals when we set out to develop this method. So thanks everybody for your attention. If you have any questions, please go ahead. And if you're interested, please feel free to check out the paper. And for any questions that you have now, I'll do my best to answer them. Thank you.
All right, thank you so much. Do we have any questions?
Yep.
You said earlier in the presentation, delta, typically about 85% of the delta values are represented by, sorry, majority of the delta values are represented by a very low.
Sure.
Low entropy. I'm close to my missed it. What is that delta represent? Is it the distance between the different points, the color
Yeah, sorry. That was all of that was strictly about position.
Yeah, could you
So,
please repeat the question for the...
yeah, sure. So the question was, we saw that these encoding of data with delta values had a very high impact and basically was able to encode a lot of the data with very few entries, but it was unclear what data this was referring to in a regular point cloud. And I failed to mention that our focus here was position, because that is usually the most vital data, for instance, for surveying or measuring distances or classifying even in point clouds. So that was our key interest that we spent the most energy on. The color afterwards, as we showed, can be compressed with fairly simple methodologies in comparison to achieve good visual quality still.
Any other questions? Yep, over here.
You could consider something like ANS, which is also as an alternate to the
We did not, and this is something that sounds very interesting. If it is really GPU friendly, I would really like to learn more afterwards.
Any other questions over here?
Do all the point cloud blocks share the same encoding table?
Come again, sorry?
You divide the point cloud into blocks. Right?
Yes.
Do they all share the same decoder table?
So the question was, we divide the point clouds into blocks, and do they all share the same decoder table? And the answer for that is yes.
Do you consider creating multiple copies of the decoder table to avoid the event configuration?
So could we make some microcopies of the decoder table to avoid this competition? Yes, we could. We found that in practice, in our experiments, there was not that much gain to be had, but definitely that's something where you could do more experimentation and get a little extra in terms of compression efficiency out of it. Yes.
I believe you said that delta compression worked because LiDAR had to have regular patterns. How does it fare with photogrammetry point clouds, which might not be as regular?
Okay, so the question was, it works with these regular sampling intervals, or for instance, integer-based data. Now, what if you, for instance, photogrammetry and your output is something that is with arbitrary, for instance, floating point precision? Can that still work? The short answer in this case is no, or not easily. So that would need to be, I would say, limited to something that is reasonable in terms of precision, so still introducing some sort of minimal intervals. Now, even for large-scale data sets, usually entries like LAS or the common LiDAR data sets, they will enforce some sort of minimum supported precision or regular supported intervals that they have for their data, which makes sense, like a precision of up to 1 centimeter. Yeah? And then basically discretize it with that. And we find that in practice this is very common, so we think that for many use cases, even if it was captured with this arbitrary precision, people will not definitely rely on it and be fine with an adaptation to make it like, for instance, this regular 1 centimeter sampling.
Okay, we might have time for one more if we have another question. Okay, great. Thank you so much.
Thank you.
What a wonderful presentation. All right, our next paper presentation is going to be on fast orientable aperiodic ocean synthesis using tiling and blending. This is coming from Nicolas Lutz, Arnaud Schottingen, and Guillaume Gillette. I think I got those as close as I could.
Good morning, everyone. Is the mic working fine? Okay, thank you. Good morning, everyone. My name is Nicolas Lutz. I'm a postdoc at the University of Sherbrooke in Canada, and soon to be a professor assistant at the University of Montpellier. And I'm presenting to you today our paper called Fast Orientable Aperiodic Ocean Synthesis using tiling and blending. Deep ocean generation and rendering is important for the plausibility of a real-time virtual world containing large bodies of water. It's not as simple as taking a plain mesh and coloring it blue though, because it requires simulating the movement of the waves and the behavior of light on the surface. The ocean spectrum is an object that represents the ocean in the frequency domain. Ocean wave spectra have been measured from real oceans using oceanographic measurements, giving us analytical expressions of the spectrum. In theory, this allows to simulate ocean waves from an inverse Fourier transform. In practice, though, an inverse Fourier transform with a large spectrum is too expensive to compute an entire ocean. Ocean generation is instead typically carried using the Tessendorf model, which consists in computing a small periodic displacement map, which is used to displace the waves, and normal map used to shade the surface, generated by an inverse fast Fourier transform of an ocean spectrum and a tide-dependent phase. So in this figure, this is an illustration of the approach. An inverse fast Fourier transform computes a small displacement map that is periodic, and then we can repeat this displacement map on the entire surface to get an infinite displacement. The resulting periodic ocean exhibits tiling artifacts, which come in the form of aligned repetitions. This is an issue for immersion, because when modeling an ocean, one does not expect it to tile on the surface. Here is a visualization of the corresponding displacement map. In the past, we have noted two different ways of hiding periodicity. The first is to mix the periodic displacement map with Perlin noise or other noises, which shifts periodic values to periodic statistics. The other one is to overlap several sub-displacement maps overlapped at different tiling scales, like in the figure on the right, which requires to compute several sub-inverse fast Fourier transforms, but significantly increases the actual period of the ocean. In our experiments, mixing a periodic displacement map with Perlin noise is either too periodic when the weight of the noise is low, or looks too much like noise when the weight is high. On the other hand, the periodicity of individual sub-displacements is still visible, especially for low-frequency waves, which tend to be the tallest. So neither solution is satisfactory. In the field of procedural texturing, the issue with periodic tiling is well known, and real-time by-example texture synthesis is a tool that is used to solve the issue. It consists in generating textures directly in the fragment shader using an exemplar as model, for which we try to reproduce the statistics or the appearance without repetitions. Tiling and blending, in particular, is a popular algorithm which consists in blending the content of 3 hexagonal tilings on the surface, like so, on a regular grid. And each of the content of each hexagon is sampled randomly in the exemplar. Our solution to get an aperiodic ocean is therefore to compute tiling and blending using as exemplar both the displacement map in the vertex shader and the normal map in the fragment shader, both being given by the Tessendorf model that is computed in the compute shader. This approach is illustrated in this figure with a displacement map that is obtained with a Phillips spectrum. By definition of tiling and blending, the resulting ocean is fully aperiodic, meaning that it does not tile whatsoever, as can be seen with the displacement map. Tiling and blending allows us to introduce another enhancement, which is to control the orientation of the waves without stretching or distortion. The orientation is fully arbitrary and is given by a flow map for additional offering control, as you can see here on the left of the video. If you're curious about how this works, it works by rotating individual tiles. We first sample the flow map at the center of a hexagon, which gives us an orientation of the waves. And we use the orientation of the waves and the direction of the wind to deduce a single angle per tile. With that angle, we then rotate the indices that are normally used to sample the displacement map or the normal map around the origin by that angle, like if you were rotating a hexagonal piece of texture. We then rotate the displacement or normal vector that is sampled around the up vector, kind of like if you were correcting a normal after a rotation of a normal map. Finally, to smoothly transition from one angle to another, we only have to rely on the blending that is inherent to tiling and blending. In our paper, we propose another enhancements with regard to lean mapping. So lean mapping is a filtering technique that allows to filter specular lobes when the surface is shaded with the Blindfunk shading model. In this figure, you can see that the correct filtering in the middle is somewhat less bright and less noisy than a simple normal mapping on the left, and that lean mapping on the right is much closer to a correct filtering. This requires an additional texture set that I'm going to call in this presentation the lean map, which represents the mean and second order moment of the normals under each map footprint. So this is a little more expensive to compute, but it allows for a more realistic ocean or a surface with a normal mapping. In 2022, Charline Grenier showed that it was compatible with tiling and blending, meaning that it is inherently compatible with our ocean. Things are a little more complicated when we want to use lean mapping with a flow map, though. And in our paper, we show that theoretically, lean mapping with a flow map will require one lean map per angle, which will therefore require an infinite amount of lean map. We also show, however, in our paper, that we can express the components of each of these lean map as a linear combination of the components of the original unrotated lean map, which is a new and interesting result, possibly not only for ocean rendering. What's to take from this figure is that if you do not correct the lean map, your specular lobe is going to look way off on the right. To assess the quality of our ocean, we use the tool known as the autocorrelation function, which represents the second order moment, or rather the centered normalized second order moment of a stochastic process. If you don't know exactly what this means, the autocorrelation function can actually be expressed as the inverse Fourier transform of the power spectrum, and therefore an ocean spectrum. When we compute the autocorrelation function of a real ocean, we notice that it rapidly converges towards zero when increasing the distance, following this shape. When we compute the autocorrelation function of several ways to compute an ocean, we notice that ours is the only one that has such a shape where the autocorrelation function rapidly converges towards zero as the distance increases. This shows not only aperiodicity, by definition of the autocorrelation function, but also a better fit with a real ocean on the second order moment. If you're curious about how this is computed, you can check out this previous article of mine. The size of the synthesis tile, interestingly, has a direct impact on the autocorrelation function, where having large tiles slows the rate at which the autocorrelation function reaches zero. Other than that, in terms of look, having tiles that are too small introduces high frequency waves due to rapid shifts from the content of one hexagon to the next, whereas having tiles that are too large reintroduce local periodicities due to each hexagonal tile encompassing several periods. In terms of computation times, there are a few interesting things to note. First, we did not change the generation of the initial tile, meaning that the computation time are the same. The rendering is a little slower because the displacement map and the normal map respectively both require the final displacement map both require to sample 3 times the initial displacement and normal map respectively. It is much faster than multiple sub-displacements, although we do note that in theory, when using multiple sub-displacements, you could just cut the frequencies that are not used for the sub-inverse fast Fourier transforms. The flow map in our experiments costs about 0.1 milliseconds more when in use, so it's really cheap. Lean mapping is quite more expensive because it requires about 1.4 milliseconds when not optimized. Our application is not exactly optimized, and one of the possible optimization, which is pretty important, would be to encompass the normal map inside the lean map, which would cut the computation time of lean mapping by about half. What's to take from all of this is that our ocean is very little more expensive to compute, but it's the only one that allows for a true aperiodic ocean and with a better second order moment like I showed you earlier. Now there is an interesting limit to note regarding variety, which is linked to tiling and blending itself. In tiling and blending, variety is only as high as the exemplar, so in this case as the original tile, which leads to repetition. So in this figure you can see that I have circled several displacements which kind of look a little bit the same. Now in practice, repetitions are hard to see for 3 reasons. The first one is that the displacements are actually blended with other displacements from the original displacement map, which means that, as you can see, they're not always exactly the same. The second reason is that you're not actually visualizing a displacement or normal map. You're rendering an ocean surface, which can be boiled down as a bluish mesh with a displacement. So repetitions are harder to see. And finally, if you were to try to spot a repetition, it would be hard to do because the animation makes it so that by the time you look from one place to another, the repetition is already gone. So interestingly, for this application, tiling and blending has less visible repetitions than, say, for synthesizing a static texture. There is another interesting discussion to have about artistic control, which is related to the fact that when using multiple sub-oceans, you have an additional offering control due to the fact that you can control the individual sub-displacement map individually and normal map. For instance, you can increase the weight of the low-frequency waves or the height, which to my knowledge is something that is done in Sea of Thieves. Ultimately, our synthesis is compatible with any periodic map, which means that it is compatible with, which means that we can use it on any or all sub-oceans. For instance, you could decide to only synthesize the low-frequency waves and keep the authoring control that multiple sub-oceans allows you to have. In conclusion, we have presented 3 main contributions: a new fast and efficient way to periodically tile an ocean using an existing algorithm in texture synthesis, a way to control the orientation of the waves with a flow map without stretching or distortion, and we showed how to execute a lean mapping when using a flow map. In the future, we would like to hasten the generation of the initial displacement and normal maps, for instance using noises that are well known in texture synthesis or procedural texturing, such as Gabor noise. We would also like to provide more control, for instance by controlling wave amplitudes using different wave spectra or especially varying wave spectrum when according, for instance, to the distance with the coast or special weather conditions. Thank you for listening to my presentation.
Excellent. Do we have any questions?
Did you consider just taking all this and replacing all of that with AI?
Well, sure, why not? But the issue with AI right now is that it's simply not as fast as just having a good analytical expression and just evaluating it. So tiling and blending right now, it's still faster than any AI model. And since I'm not an expert in AI, I'm not going to look for a process that is faster than that.
Any other questions? I had one when I saw the flow model or the flow field part of your contributions. I thought, hey, this might be interesting. What do you think the limitations would be if you had a flow map that came from, let's say, an atmospheric model to try to give some physically based, like physics simulation plausibility to this? Like, what kind of issues or limitations do you think there would be with that?
Can you repeat the part with the physically based?
Yeah. So I mean, I come from scientific computing background, so I deal with atmospheric models where they're computing wind. And of course, once you have wind, you could have a flow field. With a flow field, you could be visualizing how the ocean might look under such wind conditions. Do you think there's like interesting possibilities there or issues that come to mind? I know this is on the spot, but what would you think?
Well, what I'm thinking right now is that the flow map that we propose does not actually look very realistic. You can see that the ocean is doing some kind of S right now. It's more for spatial offering control, for instance, if you want to have a cool ocean like this that just goes to the center. For instance, if you have, let's say, a singularity in the world, who knows? Right now, I don't know exactly what you could do with a more physically based model. I think it would be interesting to try. We haven't gotten very far with the flow map. One thing that we didn't even try to do, for instance, yet, is to have a flow map that you can change in real time. That would be interesting to do, and that would also correspond to reality more.
Very good. Any other questions? Over here?
Yeah, so assuming you have a very large velocity in the flow map, I think we need to start suffering some.
Can you speak up? Sorry.
Yeah, so I'm saying if you have very large velocity across the flow map, I think we need to start suffering some stretching artifact flow methods.
I'm not sure what.
I think to understand your question, if you had large velocities in the flow map, what kind of artifacts that would generate?
Like stretching artifacts or other distorted
Right now, in this application, the velocity of the waves is fixed. It's determined by a user-defined parameter. So when the flow map that we propose is only a bunch of directions. They're not they don't actually have a velocity tied to them, and I'm not sure how that would work. Because the issue is that the animation is entirely carried in the Tessendorf model. So we're just taking the Tessendorf model and synthesizing it. So in theory, you would have to do something else, like having several animated oceans and blending them, for instance. So right now, what you propose isn't quite possible.
All right. Quick question.
Another quick question. How about the wind in the ocean? Do you consider if we have a lot of wind over the waves, and that would change the appearances somehow?
Right now, when using the flow map, the wind doesn't come into place. It's not. It's irrelevant, and it's irrelevant. So right now, the wind can't influence on the ocean when you control it with a flow map. What you would need to do is probably compute two oceans and blend an ocean that is subjected to wind with an ocean that is subjected to a flow map. That's at least how I would do it, and maybe control the weight with maybe a spatially varying map. That would be possible. But right now, with this application with a single ocean, it's either use a flow map or use the wind condition, or use the wind. Although you could obviously continue to explore this direction.
Okay, I think we're out of time. Let's thank our speaker. Okay, our final paper presentation is on parallel spatiotemporally adaptive DEM-based snow simulation. This is coming to us from Simon Andresen, Linus Ostergaard, and Prashant Goswami. Take it away.
Good morning. So I'm Prashant, and I'll be presenting our paper. I will start with the background. Snow simulation is essential in computer graphics applications. In movies, in computer games, there are games now that are dealing in snow settings. And on the other hand, if you look at a number of SDKs that are dealing with physics, snow is missing in most of them. It's because it's computationally intensive, and it has properties that other materials do not have, like it can get compressed, it can melt. So for example, with fluid simulation, those things don't happen. So there has been some work, as I will discuss in a few moments, on snow simulation in computer graphics, but the focus has been accuracy. And our group has been working on accelerating snow simulation so that it could be used for real-time applications. So if I quickly sum up the work in the computer graphics community on snow simulation, the first paper was in SIGGRAPH 2013, the first prominent paper. And it was semi-Lagrangian, based on a semi-Lagrangian model. And then there was a paper in 2020, also in SIGGRAPH, that was based on an SPH model. Meanwhile, we have been also working on the DEM, or discrete element method, for snow simulation. We have this real-time particle-based snow simulation on the GPU, and an improvement of that paper that utilizes an iterative approach. There's much more work on snow and ice. If you would like to check out, you can look at this state-of-the-art report that was published in Meteorographics this year. On the other hand, if you look at adaptivity in computer graphics, it's a very well-known phenomena. Even in simulations, if you look at SPH simulations, for example, they are trying to have spatial adaptivity in a lot of works. On the other hand, if you look at snow, this work is only starting to warm up. So, for example, to propose data structures that can leverage GPU more efficiently, or to use regional time stepping in a grid-based framework, which is applying temporal-only adaptation. So those kind of works have started to come up even for snow simulation. So our contribution in this method is that we are going to take this our iterative discrete element-based solver, which is already very high-performing solver for snow simulation. And we're going to apply spatial and temporal adaptivity to that simulator to accelerate it even further. And we are doing all this on the GPU. So most of the things that we do to accelerate this solver, because this base solver is also on GPU, we accelerate the solver also on the GPU. That includes merging and splitting and region determination. So to introduce you to the base iterative DEM solver, the way it proceeds is that it assumes that all particles begin as snow particles with air entrapped in them with a certain radius, and as the air is squeezed out of the snow particles, they become ice particles. So there's a concept of compression. And of course, there are normal and tangential forces that keep particles away to reduce the overlap between particles. And there's also something that's not in any other of the other frameworks, that is bonds between particles, because bonds between snow particles are very important to capture the right behavior. So the idea here is that to put it all together in a loop and to solve in this iterative loop such that the constraints are respected and the overlap is as minimized as possible, because these particles don't interpenetrate in real life snow grains. So you have these two extremes of particles, and then you can have any particle that's in between these two. So which is determined by eta, or the radius of the particle, and one can interpolate quantities like Young modulus and cohesive strength based on these two extremes and depending on eta. So what do? We take the basic physics solver of the base iterative DEM solver, and then we identify regions that are spatially or temporally adaptive and where we can get some benefit by applying spatial or temporal adaptivity. We compute this activity, we assign these regions those activities, and then we start with particle splitting and particle merging for spatial adaptivity. And at the end, we apply temporal adaptivity so that particles or regions that are not doing anything can be frozen. So one of the simplest ways to compute the activity in any simulation domain is to use the grid that already exists in the simulation domain. So here is an example. So there are these smallest particles on the which are red particles, and then these are the largest particles, which are the blue particles. So these particles pass on their activity to the parent grid cell, and then the grid cell decides on the activity by taking the most restrictive activity and then passes it back onto the bar containing particles. This way it can be done in a very efficient and parallel way. This is what we do as well to compute the activity. However, we need two different activities. One is spatial temporal. It is used by both spatial and temporal activity determination, and the other one is only temporal. So the idea behind spatial temporal is to identify visually significant regions that require a higher resolution of particles. On the other hand, temporal regions are those regions that are trying to figure out which regions are inactive, and we can get some benefit from there. And we use a fast marching method for activity propagation. So once we determine the spatial activity, we have to propagate it so that we are prepared to deal with it as something moves and we are not taken by surprise. So we are prepared for the activity. So for that we use fast marching method, and the frequency of activity computation is adjusted, which means that we do not compute these spatial temporal or temporal activities in every frame. We do that every few frames, maybe every 100 frames, and then apply the adaptivity and then do it again. So here is an example for merging. Once the spatial activity is determined using the spatial temporal activity that we just talked about in the previous slide, particles that are identified as smaller than decided activity are merged together. So here is an example. Those two red particles are decided to be merged together. So this requires that there is a search that is launched for every such particle, and this happens in parallel. So all the particles are put together in a buffer, and then a search is launched for all those particles to look for a similar particle in the vicinity to be merged. And we try to match the attributes of the particle as much as possible for this merging. So for example, the particle should not differ too much in velocity or in the state, and in the hierarchy. So it should be like the similar color of particles. And when these merging begins, we give a certain time for it to happen. That's called the interpolation process. So the merging happens slowly. The particles transfer mass to each other during these max iterations, like 100 frames, so that there's no instability in the simulation. And the final particle consists the attributes as fairly as possible. For example, temperature and mass, of course, is inherited by taking the sum of both the particles. Similarly, for splitting, once particles are identified which need to be split, for example, because they have an activity that's, now they have a higher activity than they had before in the spatial region. So those particles are tagged for splitting. So you see that for that we create a virtual particle to start with. It's a virtual particle with zero mass, which is very close to the particle that's tagged to be split, also done in parallel with all the particles put in a buffer. So slowly this mass is transferred from the big particle to that small virtual particle, and this virtual particle is moved away during these max iterations, and all the attributes are also equally divided between those two particles, like mass. For that we need an extra global buffer, which we did not need in case of merging. And some other considerations have to be made, which are mentioned in the paper, like delaying collision. So here is a picture that shows why we cannot just split the particles in one moment. Why we have to do it slowly, because even if we split the particles in just one go, there is an overlap. There could be overlap between the neighboring particles that will, make particles go everywhere and make the simulation unstable. After we have applied the spatial adaptivity by splitting and merging the spatial temporal regions, we come to the temporal only adaptivity. So as I said before, that we need an additional activity on the coarsen grid. So we compute activity on the grid, but we use a coarsen grid instead of the neighborhood search grid, because that way we can further reduce the overhead of activity computation. So regions like, as you see, there's a lot of region in this particular scene that is actually not moving at all. Those regions do not need to be updated every frame. We can completely skip all the computation basically there. So, but sometimes what happens is that there are particles that were tossed up in the sky and they have a velocity of 0 before the velocity becomes again finite and the particle falls back. So sometimes those particles could be identified as inactive by the spatial temporal activity. That's why we need one more activity, temporal activity, to mark those particles as active, even like when momentarily they appear inactive. So we just identify those particles and skip most of the physics. So for this conference, I know it's very important to talk a little bit about the parallel part for the GPU part. So the spatial and temporal optimizations are globally synchronized, which means that all the particles that have been tagged for merging and splitting, they all tag together, and then they are split or merged, and then the next cycle of tagging for merging and splitting begins globally. The same goes with the temporal optimization. We have CUDA threads because we have implemented this using C++ and CUDA and GLSL. So in the CUDA threads, we have two kinds of threads. One is per particle thread, which means that every thread is given the responsibility to compute physics attributes for each particle. But sometimes when we are determining the activity for every grid cell, even those are that is done through threads, CUDA threads, and one thread is launched per grid cell. There are certain components, certain inexpensive components in our simulation that could not be completely parallelized. One of them is FFM, which is the marching method to determine the regions for the next frames. So we do it in a sequential way. And the other one is when for merging pairs are identified, sometimes it requires atomic operations for bookkeeping. So those two parts are not completely parallel, but we have verified in our experiments that they do not have a very high computational footprint. So about the results, we have tried our method on various scenes, and as you can see that the temporal method provides temporal only optimization provides anywhere between 1.18 to 1.4 times speed up. On the other hand, the spatial method can provide higher speed ups, especially with increasing number of particles. So we have tried it with 3 million particles on GPU. On the other hand, if we combine both the spatial and the temporal adaptation, we can get speed ups which are like 3.5 or above. So we hope that if we have more particles, 4 million, 5 million, we will get higher speed up. Before I show you the videos, also to bring this up here, that the kernel cost, the various kernel costs. So as we see that physics is still a very prominent part in terms of the CUDA kernels, the time spent on the CUDA kernels, and the overhead of the adaptive, whether it's spatial temporal or spatial temporal, is not that high. It's very low rather. On the other hand, the GL buffers, the transfer of buffers, CPU GPU transfer is still is a very prominent part that could be taken care of in future implementations. So let me show you this video. So what you see here is the base simulation with 1.15 million particles, then the spatial only, temporal only, and spatial temporal. And I show it here together, all of them together, so that it's easier to see that there are, the simulations do not look exactly similar. There is a difference. You see that in another scene where the speed up is about 3 times. So as as a region is marked to be split or merged, there is some additional activity that's happening for merging and splitting, and that's why there are some, extra what you call artifacts or unrequired or undesired activity in certain regions. But on the other hand, if you look at a number of computer games, especially that are dealing with snow as a mass, not like for some micro level interaction, this kind of activity might be tolerated. It might not be something that's kind of a very big deal. And here I kept this scene for the end to show that if we have like the micro level interaction like with shoes, then this pronounced activity is the most noticeable because of merging and splitting. Although we do get a speed up, and if we zoom out, maybe it'll be more acceptable. So to sum up, we have presented our method that can provide speed ups of more than 3.5 times in some cases with 3 million particles by applying spatial and temporal adaptation. The quality of base simulation and the temporal adaptation only are very similar. On the other hand, the spatial adaptation causes some, creates some additional effects which could be perhaps minimized in future work. It could also be that the discrete element forces are different in nature from SPH forces, smooth particle hydrodynamics forces, and they have smaller smoothing kernel. That's why these forces have probably a different nature, and that also needs to be incorporated into some future work. And finally, this CPU-GPU overhead could be a critical factor in some cases that could be minimized by trying it on Vulkan on DirectX 12. So thank you so much for your attention, and I'll be happy to answer your questions.
All right, we have time for maybe a couple of questions right here.
How inactive particles are identified?
So particles that do not move, which have like a zero velocity. And we keep identifying those particles every few frames and tag them. And then if they are going to get active again, we activate them using FFM, fast marching method.
What happens when two particles are supposed to merge, and then there is an event like collision with something, and then they move apart? Because your merging process takes like a few iterations. What happens if during the merge process, like the particles move apart?
But I have not been able to completely hear it out. Could you?
What happens when two particles that are supposed to merge move apart during the process?
So the question is that what happens if two particles that are supposed to merge move apart before merging happens, right? So if the physics is working in the fine way, the way it's supposed to work, the particles should not get that close to each other. Nor move so far away from each other during a small span of time after they are identified. They should move slowly, right? And that slow movement should be still make it traceable to identify which particles have been marked for split merging together. If particles move away that quickly, then there's something wrong that's happened. So this global iterative loop is actually making sure that any particles that have overlap, they are moved apart from each other in a synchronized manner globally. So all particles, there was a paper a long time back, it's called Predictive Corrective Incompressible SPH. So the idea is taken from there, but if we do it globally, it could be done together for all the particles and in a very efficient manner. So that's what we do.
Right here?
You obviously probably need some different visualization, but have you considered or what would be the challenges of applying this method to like other materials such as like transitions from like smoke to fire?
So what you're asking is about the transition from soft?
The applicability of your method to other materials.
So the question is that what is the how does it go for other materials for a similar method? Yeah. So in the related work slide, we talked about many methods in computer graphics with SPH simulations. People have tried like the spatial adaptation a lot. One of my previous work has also tried temporal adaptation in SPH. So it seems that I think in every kind of method it has been tried. But because discrete element method is slightly new in computer graphics for snow simulation, it was not tried. So I'm pretty confident that it can work for 95% of the methods, And the only thing is that would it be parallel? And here in this case, if the base solver is parallel, we have been able to make it as parallel as possible, and that's why. So the base solver is the fastest existing snow simulator, and now you add up the speed up of 3.5 times here. So I think there are very high chances. That's my guess.
Okay, I think we have one more question over here to the right. Over here.
You mentioned that you guys were globally synchronized. What percent of the time are threads spent idling and waiting for the synchronization?
So the synchronization is happening when CUDA kernels are launched. So there is no extra overhead for synchronization. You just wait for the CUDA kernels to be finished as usual, like you do that in every frame. And but the reason why I brought up that point was that you can have the splitting and merging, which is temporarily or let's say in a certain region synchronized, not globally synchronized. But we do that in a globally synchronized manner, and it works very fine.
Great. Well, let's thank our speaker.
Thank you.
And the best part is, HBlock is simple to implement and integrate into existing ray tracing frameworks.
Denoisers are used to blur away noise from Monte Carlo methods such as path tracing. But too much noise and you'll be left with a complete mess. What if you could explicitly control noise of a path tracer through intelligent use of a radiance cache? That's what this paper is all about. By collecting variance estimates across the scene, we try to make just the right termination decisions to reach a certain variance target. We also look into estimating bias of radiance cache cells so we can make a more informed decision. So if you're interested, please have a look.
CPAT generation strategy is an important aspect for method utilized meaningful walk. It greatly affects the performance and efficiency of the algorithms. Many prior works utilize unidirectional exploration from shading point to generate CPath, which is not that efficient as sampling caustic compared to bidirectional methods. So our method introduced bidirectional information through reusing spectral chain from nearby photons, which allow us to efficiently sample multi-bounce caustic and reduce variance compared to previous methods. You can find more details in our paper, Photon-Driven Meaningful Sampling. Thank you.
Rendering vector graphic strokes correctly is challenging even on a CPU. Our method does it efficiently in GPU compute shaders. First, we subdivide cubic Béziers into Euler spiral segments using an easy-to-compute error metric. We approximate the parallel curve of each Euler spiral segment, subdividing into line segments to meet an error tolerance. In the continuous limit, the density of subdivisions is a simple mathematical function. Our method then lowers the stroke outlines into either line or arc segments, your choice. Adding evolutes gives strong correctness even with high curvature. We stitch together the individual segments into a stroke outline, all in parallel for high performance on a GPU.
Ray tracing can significantly improve the lighting quality of photorealistic real-time rendering. However, acceleration structure management is still a challenge in large and highly dynamic scenes. We present a novel culling method specifically for real-time ray tracing that counts the number of intersected light paths per model. Dividing the scene spatially allows us to cull entire regions that are not important. With this, we only maintain acceleration structures for models that are crucial for the ray-traced lighting. Finally, we propose a hybrid path tracing pipeline, making aggressive use of our culling algorithm to achieve real-time performance even in large scenes with many animations.
Our method caches radiance over the hemisphere at primary and secondary hit points. Incoming radiance is cached in the so-called primary cache. Sampling the incoming radiance for the primary cache, we allocate secondary caches at the required secondary ray surface hit points. At the secondary hit caches, we sample direct light sources and store the outgoing radiance in the caches. To get multi-bounce global illumination, we let the secondary caches sample each other. The primary caches are also able to sample environment maps and emissive surfaces to account for direct illumination. Our approach supports model-bound sky, glossy and sharp reflections, and efficient multi-viewer rendering.
We accelerate NeRF rendering by caching and reusing view-independent latent codes within a frustum volume. Sampling this cache from nearby viewpoints allows for efficient re-evaluation of view-dependent effects and blending with resampled cache misses. We propose several improvements to ensure fast, high-quality rendering from such a cache, like inducing linearity into the latent codes and encoding view directions with our novel cone encoding. Our method achieves speedups of up to 2x for real-time and offline rendering of high-quality video sequences for our instant NGB-based model.
Monte Carlo path tracing is a rendering technique primarily used for offline image and video generation in the movie industry and medicine. Enhancing the quality efficiently involves applying denoising to the Monte Carlo estimates. We propose a fully analytical method based on sample convergence curves. It blends the unbiased estimate with its denoised counterpart, effectively recovering fine details that may be lost during the denoising process.
Rendering is becoming increasingly complex. To strike a balance between quality and power consumption, we need a method to measure the rendered quality of the current frame. Given a real-time rendered game image, we need to detect the quality of the rendered image using aliasing detection. The number of aliasing tiles indicates the quality of the current rendered image. We proposed a multitask method that leverages image space information and temporal data to enhance our aliasing predictor. Our method makes predictions more precise and temporally stable.
Using voxel hierarchies as a generic 3D scene representation makes remarching, anti-aliasing, and LODs easy. The drawback is a huge amount of memory required, even with empty space compression. Still, our previous work showed that by using a ray-guided cache to produce and store only visible voxels on demand, it is possible to work through very large and detailed worlds in bounded GPU memory, and with real-time performance. However, on-demand production of data during rendering is still challenging in terms of GPU synchronization and starvation. By leveraging dynamic parallelism, we are able to dramatically improve GPU utilization and achieve a 2x gain over our previous method.
Volume rendering is very popular in computer graphics. Despite this popularity, we do not have access to hardware-accelerated volume primitives. We propose to use tetrahedron as a rendering primitive, and we use mesh shader to encode them such that they can be rasterized while maintaining volumic information. With our method, each fragment receives the depth of the front and back faces of a tetrahedron and does its shading within those bounds. Our method can be used to compute the optic depth of complex scene in a single pass and to invoke marching algorithm. Our method fits in a single shader and can be easily integrated into a rendering pipeline.
We present a party our new GPU ray tracing framework. It has minimal setup and simple syntax. It provides high-performance ray tracing, thanks to carefully optimized bounding volume hierarchies. It also supports advanced rendering features, such as multi-level instancing. And it was already integrated into some of the professional renderers.
Are leafy scenes bringing down your ray tracing performance with all that any-hit shading? And do you have a bit of memory to spare? Then just use opacity micromaps and improve your ray tracing performance by up to 26%. Now more than 110 times smaller than before, thanks to our novel tree-based compression method. Come to our presentation to learn more.
DGF is a geometry compression format enabling ray tracing of nanite-scale scenes on future AMD GPUs. Think of DGF like texture compression, but for geometry. Applications will bake their micropolygon geometry clusters into DGF at level baking time, like with texture compression today, but DGF blocks can also be encoded at frame time. DGF blocks are 128 bytes and store up to 64 triangles. The BVH builder can treat each DGF block as a single primitive, leading to significant reductions in BVH build times and memory footprints. DGF uses our generalized tri-strip format that supports left and right turns, restarts, and ears. The blocks can be decoded in shaders or in fixed function hardware to allow rasterization of DGF geometry as well as ray tracing.
Introducing real-time procedural generation with GPU work graphs. We are the first to utilize the new GPU work graphs API to fill a scene in real time with lots of geometry. Because our system runs entirely on the GPU, everything generates in real time. Therefore, users can directly influence the generation. In our paper, we showcase dependent and recursive market generation, IV generation utilizing hardware ray tracing, and dependent and cult frustum clutter generation. Check out our HPG paper if you want to learn more.
Large-scale LiDAR scanning generates billions of points, which are challenging to visualize. When trying to store and render such massive point clouds, we encountered errors telling us that our GPU does not have enough memory. Well, you can either buy the latest GPU, or you can choose our approach. Our carefully crafted compression scheme allows you to fit these datasets on the same GPU and enables real-time rendering. We use Huffman coding for lossless compression, reducing memory utilization by 4x. This makes David Huffman very happy, and GPU vendors very sad. We bring the ability to visualize massive point clouds in real time on commodity hardware. For more details, check out our work. Thank you.
Ocean generation is typically carried by computing an inverse fast Fourier transform over a small sample, then repeating that sample. This technique often generates unnatural tiling artifacts, breaking immersion. We propose to completely remove periodicity by synthesizing the animated ocean surface in real time using texture synthesis. This approach allows us to control the orientation of ocean waves without stretching or distortion.
This paper applies spatial and temporal adaptivity to an existing discrete element method-based snow simulation on the GPU. For spatial adaptivity, visually significant spatial regions are identified and simulated at varying resolutions. To this end, we propose efficient splitting and merging to generate adaptive resolution while maintaining the simulation stability. We obtain further optimization by skipping computation on temporally inactive regions. We demonstrate that a speedup of 3 times or more of the original non-adaptive simulation can be achieved on scenes containing about 3 million particles.
All right, I look forward to it.
Hello. Let's.
Just a quick announcement for everyone. We are about to tally the best paper awards, so please bring your ballots over to the clear plastic box at the reception, the front registration desk. So thank you very much.
Before the keynote.
Before the keynote.
Sorry?
You're doing the announcement after the keynote, is that?
Oh, the announcement, yes. Well, not who? Jacko will be making the announcement.
Thank you. I'll be frantically updating.
Okay, hello. Let's start our last part of the conference, last session. So please, after this keynote, remain on the room because we are going to make some announcements, the prize announcements, and also we will announce where's going to be HPG next year. So it's, please stay here after the keynote. Okay. So let's start. It's an honor for us, to HPG, to have as our third keynote John Burgess. I don't know if that's correct, your pronunciation, John Burgess?
Burgess, yeah.
Burgess. So it's, John is a vice president of GPU architecture at NVIDIA, where he has been contributing to GPU design for 20 years. His experience spans memory systems design to streaming processor cores, including tensor cores for AI and deep learning and ray tracing cores for professional visualization and gaming. John received his PhD in physics from the University of Texas at Austin, where he has studied nonlinear phenomena such as fluid dynamics, pattern formations, and chaos. So thank you very much, and let's give a huge applause for.
Can you hear me? Ah, yes. Well, thank you for the introduction. Let me start by saying that I've really enjoyed hearing about all your research this weekend. I always find it fun to see what types of problems people are trying to solve, what they're spending their time on, so I appreciate it. So today, I'd like to tell you about the acceleration of AI that we built into NVIDIA GPUs, some of the challenges we had to overcome, how this capability relates to graphics, and my perspective on where it might lead. So there's no denying that AI is starting to transform how we think about graphics, influencing content creation with generative AI, providing new compressed representations like NeRFs, and improving the performance and quality of rendering. But the reality is that AI has already disrupted real-time rendering on consumer GPUs for hundreds of thousands of gamers and for years. Hopefully you had a chance to see Edward's hot 3D talk on Friday. But if you didn't, I'll let you know that DLSS is a software solution that leverages the acceleration of AI in the GPU to achieve super resolution, frame generation, and reconstruction, which is like denoising. And it both improves visual quality and performance simultaneously. So our goal when designing a GPU is to unlock the potential of powerful tools like AI to ensure they can make a big impact. And sometimes that's achieved with dedicated accelerator hardware. So let me tell you a bit about how this hardware capability came about. For context, because not everybody is soaking in GPU architecture every day, let's do a quick refresher. This GPU is a sea of programmable cores, a memory system to keep them fed, a way to schedule work onto them, and a series of dedicated hardware accelerators for things like rasterization, depth and blend, and video encode. And obviously the GPU is optimized for massively parallel processing. This GPU, for example, has 144 programmable processor cores. Zooming in on the processor core, the programmable core, which we call the streaming multiprocessor, or the SM. It consists of hundreds of units of math, some local data storage, a way to access memory, and at the SM level, there are also several dedicated accelerators, including texture sampling and filtering, the RT core, which is our name for our ray tracing, traversal, and intersection hardware, and a tensor core, which is to accelerate artificial intelligence. And the way these programmable cores are typically used is that you run a program that loads data into the SM, processes on it, and then stores the results, repeat. Simple. So we already have the horsepower of all these programmable cores at our disposal. So there are several considerations we take into account when deciding to build dedicated hardware accelerators. First and foremost, we try to find a good problem to solve. And then we have to solve enough of it. So one way to do that is to implement in hardware the part of a key workload that has annealed, or will benefit the most from annealing, for efficiency reasons, for example. But when we do this, we also want to achieve something like an order of magnitude speed up, because our goal is to make the impractical suddenly feasible, so that when a developer plugs in the GPU and they use this capability, it feels like they have a time machine. The thing they dreamed would be possible someday just works. And the reason I say we have to solve enough of the problem is that sometimes it's necessary to build scaffolding to support the main idea, especially with a speed up of this size. But there are some trade-offs we need to consider when doing this. Typically, when you build dedicated hardware acceleration, you gain efficiency, but you lose flexibility. So to mitigate this trade-off, we try to define an abstraction, often a developer API, that lets the hardware evolve under the hood and provides the possibility for other IHVs to implement their own solution to the same problem, and developers' code doesn't have to change when switching between GPUs or between generations of GPUs. A second thing we do to mitigate this trade-off is to provide a slower but flexible fallback path. Another consideration of the trade-off to think through is that adding dedicated accelerators can drive innovation, because we're building a foundation upon which people will build further solutions on top of the new capability. Or it could accidentally stall innovation, because if you bake an algorithm into hardware, maybe people aren't going to investigate the algorithm much more. So to mitigate this trade-off, we need to really believe in the tool that we're enabling. Even within the company, right? We need to rally different teams. There's hardware teams, software teams, verification, developer relations. And if we can't get our whole company to rally behind the idea and the feature we want to enable in the product, then how can we possibly rally the entire industry to move a certain direction? And secondly, we believe that performance of these accelerators should scale on future GPUs. If you wait long enough, programmable processors could just do the task. But if people are going to build on this foundation, you want the acceleration experience to be long-lasting. And this is why we have so many accelerators that are attached at the SM level, so that as we increase the number of programmable cores, the accelerators that they can leverage increase as well. So let's look at ray tracing as an example of these principles. Before we built dedicated hardware, ray tracing was done on the GPU and software. And arguably it was already accelerated, right? Because faster than a CPU. But we looked at the workload and realized that large portions of ray tracing software had annealed. Everybody was doing roughly the same thing for a large portion of the workload. But that portion took many thousands of instruction slots per array. It wasn't particularly efficient. Excuse me. So we took that portion of the workload and we built a dedicated hardware accelerator for it, which we called the RT Core. This involved special purpose hardware for box intersection and triangle intersection, of course, but it also involved acceleration structure traversal and fallback paths to the SM to do programmable operations. With this hardware, we achieved greater than 8x performance improvement versus GPU software ray tracing. And so if we take this example and review our considerations I just went through, we found a problem that was worthwhile to solve, or that we felt was worthwhile to solve. We achieved a big speed up. We solved enough of the problem. We helped build an industry standard API and a programmable fallback. And we believed in it enough to try to move the industry over years and generations of GPUs in this direction. So that's the ray tracing example. What about artificial intelligence? If you're not soaking in the topic of AI every day, like I end up doing these days, it may just be a buzzword to you. So here's one way to consider its usefulness. Artificial intelligence is just a toolbox, right? And it contains a variety of new tools called neural networks. One of the simplest neural networks is a multi-layer perceptron, or MLP. And the idea is that it computes weighted combination of inputs into temporary values, we call a hidden layer, and then you do that again, combine those inputs into another hidden layer, et cetera, until you get to the output. And then the weights for this weighted combination are incrementally adjusted during training against the desired output. And then they're frozen and simply used during inference to perform a task at which the network is now an expert. A more complex example, a convolutional autoencoder, is shown in this cartoon. You have to forgive the cartoons. And it consists of an encoder-decoder pair, where the encoder is iteratively performing convolutions and downsampling to build up a multi-scale representation of the input data. And then the decoder can take that representation and project it back to some other representation, an image, for example. An even more complex neural network is a transformer. And this is arguably the most important neural network in the world right now, because transformers are the basis of every large language model you've heard of, including ChatGPT. Now, there's even more complexity in this neural network structure, but I'm not going to go into positional encoding and mass multi-head attention today. You're welcome. But I do want to point out that it also has an encoder phase on the left and a decoder phase on the right. And one thing that's interesting about this transformer is that the output of the decoder is fed back in as an input to the decoder, shifted, so to allow it to process time series of data. So it can understand and then generate paragraphs of text, for example. So these are just some examples of neural networks in the toolbox. There are many, many, many others. But some really interesting use cases of neural networks include image processing, classification, like what is this an image of? Oh, it's a dog. Segmentation and vision for self-driving cars or robotics. And generative tasks like large language models like ChatGPT, and diffusive image generators like Stable Diffusion, Midjourney, etc. Now, developing solutions with these tools is not quite like traditional software development. In traditional software development, you pick an algorithm, you code it up, implement it, test it, and make sure you got it right, and then you go through a phase of optimization to make it fast enough or small enough or whatever your goal is. But for developing with AI, you follow a similar path, but it's still different. Instead of doing algorithm exploration, you pick a network architecture, and you choose a loss function. And Pete, in his keynote yesterday, mentioned that finding the right loss function for a problem is a good place to innovate. It's very much black magic, in my opinion. Instead of coding and testing, you train the neural network, which adjusts the weights. Right? You train the neural network on curated data. This is another problem with AI development, that is a challenge, I should say, with AI development, in that how do you find the curated data? How do you make sure it's good? How do you do the curation? And optimization looks different as well. Typically, it's fine-tuning the network or doing precision quantization so it can be smaller or run faster, exploit sparsity, etc. So developing solutions with these tools it's similar in concept, but they differ in mechanism. But the tools can be quite powerful, and from my perspective, a lot of the power of these tools is that they can leverage learned latent space representations. So recall the autoencoder I mentioned before, where I said that the encoder was doing iterative convolutions and downsampling to build up a multi-scale representation of the input data. That representation is the learned latent space representation I'm referring to. And I think it can be thought of like you've done a coordinate system transform, or you've projected the input data onto an alternate basis set of functions, where computation is less expensive or information can be stored more efficiently. And all the math people have to forgive me for really stretching the envelope here with this. But I think we can look at some non-AI examples as to the power I'm referring to in this concept. JPEG 2000 compression takes this image, does a discrete wavelet transform, and then you compress it by throwing away the lowest energy coefficients in the expansion. Or recall that a convolution in real space is equivalent to a product in Fourier space. So for a large enough convolution that you need to perform, it might be less expensive to do a Fourier transform than a multiply and then an inverse Fourier transform, as opposed to doing a direct convolution in real space. The good news is, with AI, we don't have to choose Fourier space to solve our problem, or which wavelet variant is the one for my problem. With AI, this basis set is learned during training. It doesn't have to be an orthogonal basis. It doesn't even have to be complete. It can just be a dictionary of functions that it figured out best represent the data it's been shown. And to demonstrate some of the power of this, this particular network architecture is useful for image processing tasks. So things you can do that leverage this latent space representation, or you could do denoising in that latent space. Or you could perform super resolution by building an asymmetric decoder here. Once you have the latent space representation, the decoder can take that out to whatever resolution you want. So it just builds a bigger, more upscaling on the decoder side. So let's talk about how these tools are then processed on the GPU. Neural networks are typically complex layered graphs of matrix operations. But often the matrices are larger than can fit on a single SM. These aren't 4x4 matrices by any stretch of the imagination. Each layer is therefore processed by parallelizing it across the GPU. And tiles of inputs are loaded by an SM and then processed into outputs. And I've shown this in a cartoon of a single layer of a matrix operation on the right, where the input activations are the rows colored in red, and the input weights are the columns in the purple box colored in red. And the outputs processed by a single SM are the tiles shown on the green outputs. And so other tiles are worked on by other SMs, or by the same SM at a later time, for example. So these matrix operations are really the basic building block of neural networks. As shown in this cartoon, there's a phase where there's a matrix multiply accumulate, which is performing a weighted linear combination of inputs, followed by what's called an activation function, where a nonlinear envelope is applied to those temporary values. In the activation function, other processing can happen, like normalization or precision scaling. And the outputs are called output activations, which are then the input activations to the next layer in the network. So we can just compute those matrix operations in the existing SM core. Each thread in a warp a warp is a collection of 32 threads on our architecture, has a private set of registers holding the data, and feeds a scalar math pipe. In this case, I've shown an FFMA, which stands for fused floating point multiply accumulate. And a long string of these scalar ops per thread can comprise the matrix math. But we're talking about acceleration, so we really want to achieve acceleration for this building block. And it turns out you can't just drop 10x more math right here and hope for the best. It just can't be fed in the same way the scalar pipes are fed. Some limiters for making that happen are register file bandwidth. The register file is a RAM, and you can't read out of it at 10 times the rate without building something completely different to solve that problem. And instruction issue rate. If we want to do 10 times the math per cycle, we would have to issue instructions 10 times faster. And that's a whole other part of the control section of the SM that would have to be rebuilt for that purpose. So it's pretty invasive, but there are some opportunities we can exploit to make it less of an onerous problem. The first is that for these matrix operations in neural networks, it turns out that if you do it just on the SM in these different lanes, different threads, there's a bunch of redundant data being stored across these threads. And secondly, we can take advantage of the fact that we want to do a matrix operation, but we're using scalar operations here to get it done. We're doing long strings of scalar operations that then build up into vector operations and then build up into matrix operations. So to solve this problem, we implemented operand sharing across all 32 threads. This removes redundant RAM accesses, all the redundant data, to feed a large block of math shown here, which we call the tensor core. And along with that, we leveraged the fact that we want to do a matrix operation instead of a long string of scalar operations and built special instructions to do just that. So you can see in the table on the upper left that through operand sharing and special instructions, we reduced these bottlenecks for achieving higher throughput and are able to have a higher throughput of math that's effectively fed. So basically, that's the nucleus of the NVIDIA AI hardware acceleration, the tensor core. It accelerates the basic building block of all neural networks by doing a matrix multiply accumulate, implemented in parallel dot products through a warp synchronous, all the threads work together, collective operation. And it achieves a throughput of at least 8x higher throughput than the standard SM math, depending on the data type you use in the market for the GPU. The tensor core supports multiple computation shapes, which can help with efficient tiling for data movement, as well as several data types or precision for the numbers. And here I've shown an example of a shape and a set of precisions where the input activations and the weights are represented with 16-bit floating point, and the output activations are represented with 32-bit floating point, just as an example. The thread numbering shown here is just to highlight that the 32 threads within the warp are collectively holding all of the A, B, C, and D operands that are needed to process this result as a whole. So the matrix multiply accumulate is handled by the tensor core. But it turns out the uniqueness of network architectures is often between the matrix multiplies. I mentioned some of these operations before: normalization, precision quantization, and of course the various nonlinear envelopes that are applied, transcendentals, etc. So we found that processing the activation on the SM programmable core maximizes flexibility, ensuring our hardware is able to cope with whatever is invented next. I'll highlight at this point the transformer network that I showed before that's taken over the world was just invented 6 or 7 years ago. And it now is starting to run everything. So who knows what's going to be invented next? We want to make sure that our GPU is going to be the best for running that, no matter what. Another thing processing the activation on the SM programmable core allows is that we have an affinity between the tensor core and the SM. And we can exploit this affinity to leverage, for example, shared storage for efficiency reasons. So there's a bunch of other little reasons that this is a good idea. We made a similar decision for ray tracing, where the RT core that I described earlier and the SM can collaborate on ray tracing traversal and intersection as needed. For example, custom primitive intersection shaders. So over time, we've increased the throughput and the capability of the tensor core. One example is that we enhanced the tensor core to add support for sparsity. I mentioned before that during training, you set the values of all the weights for the weighted combinations in the network. It turns out that typically dense trained weights are often just 0 or very small values. The good news is that we already know the answer to the question of what happens when you multiply by 0 or add 0, and we can exploit that. So we added an idea called structured fine-grained sparsity, where you can take advantage of the fact that some of these weights are already 0, or you can round down small numbers to 0 explicitly through fine-grained structured pruning, such that you only allow 2 out of every 4 elements in this weight matrix to be non-zero. That's why it's structured and fine-grained. So doing the pruning and then fine-tuning the weights that remain, the non-zero values that remain, to ensure that you don't lose capability from the network that you trained. You're not throwing away its goodness by rounding down numbers. The fine-tuning of the weights can be done to make sure that the structured sparsity can be exploited. And so then we just compress away all the 0 values and just store and process on the non-zero data and carry around some metadata for the non-zero indices. Where were those values in the original matrix? Those indices are used to mux in the appropriate input activations, so we're not multiplying by values we shouldn't. And that's used to compute the output activation more efficiently. So because we're using structured sparsity to ensure that exactly half the values remain, we get a 2x speed up. You get 2x the tensor core throughput and a 2x reduction in the weights footprint and bandwidth at approximately no loss in inference accuracy through this trick of fine-tuning the weights as you prune. As we've increased the tensor core throughput, not just through sparsity, but just brute force, efficient data movement becomes critical to keep the tensor core fed. So on the left, I've shown the memory hierarchy for getting data from the DRAM all the way to the tensor core on our GPU. We have an operation run from the SM called load global, which goes and fetches data from DRAM. It passes that data through the entire memory hierarchy, through the L2, L1 cache, and into the register file. And then we do a store shared, which can take the register file, the data you loaded in the register file, and it stages it into a shared memory, which is a scratch pad. Because you want to use the data multiple times, you want to stage it there. And then as it's needed, it's pulled from the shared memory scratch pad into the RF register file, which then feeds the tensor core. The problem with this is that we end up using the level 1 cache and the register file more than we need to, right? We're reserving space for the return data while it's loading. And the in-flight data could be hundreds of cycles. So that's a waste of storage. So what we did is we implemented a fused load from global memory with stores to shared memory scratch pad to avoid this temporary staging in the register file storage. Now in this case, we're reserving the scratch pad room for the in-flight data, but that turns out to be much less of an egregious problem. Also fusing this into an asynchronous copy here, we've turned what was 3 reads and a write across these various RAMs into just 2 reads. So it's more efficient. And there are many more examples like this. This is sort of like building the scaffolding around the main idea that I mentioned earlier. But this is one good example that was added a generation after we put the tensor core into the GPU. So we've increased the throughput over time. And this plot shows that we've increased our single chip inference performance for data center GPUs by 1,000 times over 10 years. Now, we didn't add 1,000 times the math hardware. We made the GPU 1,000x, rounding a bit, more efficient. And that was done through building the tensor cores that I just described, as well as exploiting several things listed on the left. Number representations using lower precision data. We're able to process faster, move without running into bandwidth limits. The special instructions I mentioned. The manufacturing process, but that turns out to be one of the smallest pieces. So moving through manufacturing process over time, one might naturally think, well, that's where the efficiency is coming year after year. And it's through these other things that are actually much bigger. Number representation is a 16x enhancement, for example. And we also added sparsity that I just described a couple slides ago. Alongside this efficiency improvement, series of efficiency improvements, the model efficiency, the neural networks and how they're used is also improved. So the overall gain is actually greater than 1,000x in data centers. And 1,000x and a lot more coming was necessary and continues to be necessary because AI data centers are tackling absolutely huge problems like generative AI. Some of the chatbots we may have used are running on tens of thousands of GPUs at the same time. Not necessarily doing 10,000 problems at once, but working together on a single problem. And it's only going to get bigger. Well, it turns out that generative AI can be used to create graphics assets. So tying this back into graphics, I have an example here of a tool called Edify, which runs in the cloud, and it's a generative AI tool. And it can do nifty things like turn a sketch, simple sketch, into an image with a guided prompt to help create the image you want. So here the image looks somewhat like your sketch, but it looks a lot better. Another thing you can do is take a static image or just a photograph and turn it into a tileable, physically based material, including all of the properties like normal maps, etc. And the third example I put here is to take a single static 2D image and automatically turn it into a 3D model, maybe for rapid prototyping. So the speed of the data center can be a boon for tasks like this. Generative AI can also collaborate with other software tools dynamically to serve content for interactive avatars. So with this example, NVIDIA's Avatar Cloud Engine, or ACE, a gamer could theoretically speak to a game through their microphone, and then we use speech recognition to turn that into text, send that to a large language model to interpret the text, to generate dialogue for this particular character in the game, which then goes through another layer of text-to-speech, and then the speech audio can be fed to a tool called Audio to Face, which performs animation of the avatar's face to match the words that they're saying that were just generated by an LLM in the cloud. It's pretty wild. To me, it's pretty wild. It's exciting that people are figuring out ways to use the power of the AI, even in the data center, for interactive experiences beyond text-based chatbots and search. But even on a consumer GPU, recall the example of DLSS from earlier, which leverages the tensor cores I described to achieve both an image quality and performance improvement simultaneously. It's also very exciting in a different way. Then whether in a data center or in a consumer GPU, the AI acceleration that I described is being leveraged to achieve these enhancements. Oops. So there's another thing I'd like to highlight. We built both the RT Core dedicated accelerator for ray tracing and the Tensor Core for artificial intelligence acceleration at the same time. They were released in the same GPU. And they've continued to evolve together over generations of GPUs. These dedicated hardware accelerators, plus a ton of software, like RTX and DLSS, they've proved to have an impact greater than the sum of the parts, in my opinion. So it's really great that we put them in at the same time and they got to evolve together and work together to solve problems. The impact that I'm seeing them have is that they've really brought in the practicality of real-time path tracing by years versus waiting for generations of GPUs. Some examples are shown here, Cyberpunk 2077 and Portal RTX, another good example, Alan Wake 2. And bringing in this capability by years, is what I was describing before, it's a time machine. We made this possible that wouldn't have been if we hadn't made these investments and made them work together. So next, I'd like to share my perspective on where we might look next for AI graphics impact. And in particular, I'm talking about on consumer-level GPUs rather than in the data center. I think that AI could also make an impact on rendering tasks other than post-processing like DLSS is. And so what this means is we have to try to use AI to solve thread scale problems rather than GPU scale problems. This implies that the AI we use will need to use very small neural networks by design for performance reasons. So let's take a look at some recent research that attempts to use AI in this manner and see if we can derive an emerging trend. The first example is neural texture compression, which uses a small multi-layer perceptron to decompress stacks of material properties. There's one MLP network per material texture stack. The MLP only has 2 hidden layers, and they achieve a 4 to 16x compression improvement over standard block compressed textures. So you can have higher resolution textures in the same memory footprint, or you can have equivalent resolution in a much smaller memory footprint. The next example is real-time neural appearance models. These are small MLPs that represent the layered material parameters, and also they also approximate the scattering math for the material. So in this case, there are 2 MLP networks, one for BRDF evaluation, one for importance sampling, per material, and they have to be trained per material. Each of these MLPs only have 2 to 3 hidden layers, so they're fairly small, and they've achieved a 2 to 4x performance improvement. I think it's actually higher now, but this is what the paper says. So if you're still around this week, go see the talk. And so I think this is a really interesting step towards getting real-time performance for complex, multi-layered, really film quality materials. This example has layers of dust and fingerprints and scratches, all sorts of things on it. Really impressive stuff. It's very exciting. A third example is neural VDB, which uses a neural network to represent both the compressed volume data as well as a sparse tree topology that allows you to look up the data very quickly. So this uses 2 to 4 MLP networks per volume. Each of those MLPs has 3 to 4 hidden layers, and they achieve a 10 to 100x compression ratio for their volume data. Again, if you're here later this week, go see their talk. My final example is the neural radiance cache. This uses a neural network to encode sampled radiance information. So it's a little bit like a neural light probe. And you can see in the center of the image that adding the neural radiance caches to the path tracing improves the sample quality dramatically, which can make your image converge faster or make denoising easier. The neural radiance cache uses 1 MLP network per probe. The network only has 2 hidden layers. And the radiance probes, interestingly, the radiance probes are updated, meaning they're incrementally retrained, and queried, meaning they're just asked what an answer is, that's inference, dynamically. And this allows it to handle moving light sources, dynamic scenes. And so it's really interesting it's doing online training this way. Well, I'm betting you can guess what the emerging trend is here that I wanted to talk about. It's that these simple multi-layer perceptrons are surprisingly powerful. They're really good for data compression. They're good for approximation of complex math. And they're good at caching of complex signal data. Because they're small, performance can be competitive with traditional rendering, which makes it very exciting. People can start using these. Especially if you take advantage of some tricks for performance and performance efficiency, like layer fusion and leveraging reduced precision and sparsity. Very exciting, but there are some challenges to overcome. If every thread in the SM, or in the GPU, is running its own neural network, it's querying a neural network for its own texel value, then we have to overcome divergence, because the threads are meant to work together. So there's both execution divergence, which I just described, but also data divergence. You have to load all the weights for all these networks, and every thread needs a different set of data. And we also need to figure out how are these network inference operations going to intermix with traditional shader code. Because maybe the network won't completely replace the shader, maybe it just it's a task within a shader. And as an aside, I'd like to point out that even some of these MLP examples are leveraging the encoder-decoder pairs I mentioned before and learn latent space representations. Neural texture compression has an offline compression phase, and it's compressing into a latent space representation. So then the MLP you run at inference to query for a texel and all of its components is taking as input a much smaller texture of latent vector values. And those are fed into the network, and your texel values and all of your material parameters for that texel pop out. So it's that same power, but it's just being used, broken up into two pieces with encoding and decoding. But whenever I chat with somebody about AI making an impact on graphics, eventually they end up asking, will AI just render the whole image? It's a good question, and I don't know the answer, but I can try to highlight some of the obvious open questions that do need to be answered before we can answer the big question. Imagine you want an AI to do this. What will be the source of your high-quality training data, your curated data that you're going to use to train this to do the right thing? And if it's doing such a big task, how are we going to make it stable, temporally stable even in its output, reproducible, interactive so you could control it, real time so you can tolerate looking at it? And we have to ask this question also about how will it interact with traditional rendering? Will traditional rendering compute a simple version of the image you want? Will it have to compute some of the difficult lighting in the situation in order for the AI to get it all right? I don't know, but I think it's an area really ripe for some great innovation. There's a lot of opportunity here to learn things that nobody knows the answers to these questions. And I think that there are some exciting advancements in techniques like video diffusion models that might help us think through the problem, but probably aren't strictly the answer to this problem. So here's a still from an OpenAI video created with Sora. And it's a video diffusion model that is generating the whole image. So let me hit the animation here. When I saw this, you should read the technical report, it's fascinating, but they don't give a lot of details. When I saw this, I said, this could be a game. Like, the AI is rendering all of this. It has an implicit understanding of all the physics involved in order to generate the dust clouds, in order to make the shocks of the truck look good. Let me play it again. This was generated from a text prompt and nothing else. The text prompt was something like a truck driving down a windy mountain road that's dusty or something along those lines. But I look at this and it's generating all this foliage, and it's mind-boggling to me. But this thing probably took tens of thousands of GPUs to train, and the inference for this probably needs to be 3-4 orders of magnitude faster in order for something like this to be practical for interactive rendering. So maybe it's not the solution. It's probably not the solution. Clearly I'm torn over this. But I think there are lots of open questions. It's exciting advancements to see stuff like this happen, and there are a bunch of competitors just coming out now for Sora. And I'm going to keep an eye on this, and I think others should as well, but there are lots and lots of open questions. So, in my opinion, AI graphics is the future. Maybe not exactly what that last slide showed. But it's clear to me that AI is going to end up disrupting all industries, all fields of study. We've already seen examples just in this talk of content creation and complexity impact, of render performance and quality impact. The good news is we already built AI acceleration into NVIDIA GPUs. So we built the time machine. And the question you can ask yourself is, how can you use these sets of tools to transport the future to now? What new neural network models will you invent? What new applications will you find for them? And how will we take feedback from those and build new GPU enhancements, which then may enable the next generation of new network models? This virtuous cycle of innovation is underway, and I heartily encourage you to jump in and make an impact. Thank you.
Okay, thank you very much, John. Very inspiring talk.
Thank you.
So we have time for questions. Does anybody want to start?
Any thoughts or insights into the divergence question you mentioned, the threat divergence for graphic shading? Do you feel SER is enough there, or do other things need to change?
I think SER, which stands for shader execution reordering, if you don't know about it, is a way of extracting coherence so that things can run sort of in parallel, simply. Just to give context, sorry. I think SER is part of the solution. I think we'll have to go further than that, and we have some ideas, but it's not quite yet a solved problem. Yeah. Yeah, sure. Yes?
We can also, on the same divergence question, more in the concept of styling MOPs, different for each thread. And you build tensor units with big matrices.
That's right.
They all want different things.
That's right.
How do you see the solution to the problem?
Yeah, so this is exactly the problem, right? So one way is to use SER so that each of the threads are, hopefully, you've extracted enough coherence in execution that each of the threads is actually running the same MLP. Because lots of pixels in a pixel shader are actually doing the same thing with slightly different inputs. So you might load a unique input for a thread, but all the threads in a warp, or a collection of threads, that then feed the tensor core are all running the same neural network, the same weights, but they have different inputs, their own unique inputs.
Maybe I'm asking, like, in terms of, like you said, with every shader, you mix machine learning with traditional shading. So we're not talking about ray tracing. We say, I'm putting an LP in the shader. Each thread wants to do a different thing.
Yeah.
How do I take advantage of tensor units? Because they're not designed for this kind.
Oh, I see. You're saying because SER isn't enabled for non-ray tracing shaders?
General.
Yeah.
Your idea of MLPs, small MLPs per thread mixed with shaders.
Right. I think the only way to do that is through something like SER. We'll have to figure out if it can be extended to other shader types, compute or pixels, because it's a fundamental problem. How do you gather together enough of the work that you can use the tensor cores and get the throughput? Otherwise, you're going to be serializing through all the different things, and you don't get the advantage of the throughput. Yeah. A bunch of questions over here. Go ahead.
While NVIDIA is still dominant on AI acceleration in the GPU side, so actually there's so many startups building some own small NPU or some other big tech build their own silicon. So what kind of the NVIDIA's perspective, those kind of trends?
So I didn't catch all of that. What kind of perspective? What perspective on what?
So those kind of a lot of the potential competitor, maybe some competitor, like building some dedicated small scale dedicated NPU hardware, something like that. So those kind of company, NVIDIA's strategy or something.
Are you talking about in other GPUs, or are you talking about
NPU? Yeah, so it's dedicated hardware.
Yeah, not dedicated hardware embedded in a GPU, just general dedicated hardware
not,
just
not,
for this
not
problem.
dedicated hardware inside the GPU, only the dedicated hardware.
Yeah. The problem, I mean, this is my personal perspective, but the problem I see with dedicated hardware that isn't tied to a GPU is that you lose that entire ecosystem that you can use to do all the things around the neural networks that you're using, right? And that's why we prefer having it pretty tightly coupled so that you can do programmable code on an SM and then go to the tensor core, then go back as often as you need to for your particular problem. And so somebody could go out and build their own dedicated hardware that just ran convolutional autoencoders, right? But how are you going to do all the other stuff you need to do?
So NVIDIA does not feel any kind of threat.
We feel threats from everywhere. Only the paranoid survive. It's so true. And we behave that way. Like, there's lots of smart people everywhere, right? We don't have that hubris. So I think that some people, some niches will find, sorry, let me say the sentence again. Some competitors that are deep diving into particular very dedicated solutions for really hard problems that are important, they're going to have their own space. They're going to have their own niche. But if you need it to be programmable, if you need CUDA in your data center and you need that programmability, it's our intent to make sure that that's the best experience you can get is on our GPUs. Does that make sense? Yep. Okay.
Case
Yeah.
for me and you. I've got a question related to that philosophical idea of when do you be programmable versus when do you commit to a particular format. You had an insightful slide on when and how do you build dedicated hardware. And you pointed out that when you when you commit to a hardware solution, you might be accelerating innovation and you might be foreclosing innovation.
Mm-hmm, right.
And you prefer to keep the hardware details hidden behind an API so that the hardware can evolve separately from the problem space. Right. One counterexample of that came to mind was texture compression. Mm-hmm. where the format is exposed publicly and agreed on industry-wide. Right. And maybe this is an example of where innovation has been foreclosed. And I'm wondering, what would your philosophy be? How would you apply these observations to the innovation shown later on of structured sparsity? Mm. And forgive me, I don't know that technology well. I don't know whether that's done in the driver. Or are you applying loss to the user's matrix? Or does the user apply that loss by rounding things down to zero? And what do you foresee in terms of APIs, et cetera, for handling sparsity and so on?
Okay. Lots of good questions embedded in that. So, yes, it's true that texture compression became sort of baked, and the dedicated hardware maybe means that people aren't spending so much time coming up with new things. But the neural texture compression, I think, is an example that completely elides the texture unit. It's, you're looking up individual texels. There's no filtering involved. You have to do stochastic filtering. And someone could implement 16-tap texture in software if they wanted to. There is a programmable fallback. You don't have to use that hardware, but it's a lot slower. So it becomes just a trade-off. If it's more important for you to have 64-tap in ISO, you can go get that done with the program instead of using the hardware. And it's going to run slower, but that might be not as important to a user, depending on their problem. For the fine-grained sparsity, the typical case for using that is that the user would need to be aware of it. And because you have to do, or it's probably likely that you have to do the fine-tuning to update the non-zero weights to make sure that you don't lose the expert level of your network that you trained when you started pruning. So I don't think it's necessarily something the driver would do under the hood. Now, maybe something like that could exist. Maybe it already exists and I'm just not aware of it. Someone could opt into that and say, I'm willing for you to make it lossy. As long as it's close to what I trained, I'm fine. But if it runs twice as fast, that's all I care about. There might be cases for that, and for all I know, we already have software that does that. I don't know. I don't know how to answer the part about whether there's an ABI to be built or an API. Maybe. Lots of people work through libraries that are provided by the vendors, right, including NVIDIA. And if there's an abstraction to be found there for fine-grained sparsity, I'm sure we'll look at it and figure out whether there's something that actually allows innovation or alternate implementation, or whether it's too specific to actually abstract away. Yeah. Did I answer all of them?
Perfect.
Okay, good.
There was one more question. Oh, here.
So the RT core and the Tensor Core are fascinating, super effective, will continue to co-evolve in fascinating ways. I wonder if you'd like to go out on a limb and predict what the next disruptive accelerator might be on the future.
Wow, haven't we done enough? Let me think about that.
We won't hold you to it.
You know, I actually thought, I don't know, upset some of my colleagues in the room. Okay, I don't want to talk about any future product or anything, but until I saw the neural appearance models, they're sort of like neural materials, until I saw that research start to form and work, I spent a lot of time thinking about how to accelerate materials. Like, is there an amazing Uber material, the Arnold shader, or something that could, take some complex thing with 50 inputs and build some dedicated hardware that just blasts through it, or samples multi-layer with Monte Carlo or something, position-free Monte Carlo or something. And it led basically nowhere. But I think there's not an obvious next disruption that's going to come from dedicated hardware that I can see. I think the next disruption is going to be about, and why I gave this talk, is going to be about using the tools we've just enabled to take that next step without needing hardware, because the hardware is already accelerating the building blocks from which we could build something new and exciting. And I think the neural appearance models thing is a good example of that. We already built the hardware. We just didn't know that it was good for that until we tried. Does that help? Okay.
There was someone.
What are the prospects for having the GPU issue in GPU autonomy, things like work graphs, as opposed to relying on the CPU to issue the work to the GPU?
Yeah, I think it's pretty common to be CPU limited when using a powerful GPU, and that's a shame. I think word graphs are going to be good for getting around that problem. But I think that's just the very first step, right? I think word graphs are going to be powerful as well to do more complex work management on the GPU itself. Making the GPU self-sufficient is sort of the first step that word graphs is trying to help get over that activation energy, right? But once we get over that, then I think it's sort of unexplored territory. So I think there could be some exciting stuff there. Things we might not ever afford to do in a driver, you could do on the GPU. And some things it just won't make sense for. So we'll have to see, I think, how it works out. So I don't really have anything really concrete to add there other than just hope. Yeah.
Yes, please. Yours.
How do you make that trade-off? Is it just market research? Is there some element of hopefulness involved in that?
Well, I think it came down to a few things. One that I mentioned before is that if we're going to add an accelerator, it better really accelerate. Like, you better get something like 8, 10x, something like that, maybe more if you can. If you can't get that much, if it's going to be 10%, why bother? Just, convince somebody to increase the clocks on the GPU and it'll go 10% faster. Put a better cooler on the thing or something, overclock it, you're done. So that's one thing. It had to be big enough to be exciting, in other words, right? But When we first came out with the Tensor Core, I got asked, I think it was SIGGRAPH 2018. After that, and I was meeting people, and somebody asked me, so how much area did you spend on that? And I said, just enough to be exciting. Right? It's actually less than you'd think. It's probably much less than you'd think. And something similar for the Tensor Cores. It was giving a big enough speed up. It costs what it costs. And so if we want that speed up, that's what we do. And sometimes we have to. Our CEO is sort of known for saying that NVIDIA goes after $0 businesses and then creates huge business out of it. And so there's a little bit of leaning forward into the future that we try to do when we're making these decisions about what to try to enable and make exciting next. Where there are no workloads that we could use practically that would show us the value of adding these things. We have to use some vision and make some convincing arguments internal to the company, et cetera. It's not straightforward because there is risk and there's cost. Simply adding more programmable cores would have gotten us a few percent more performance. That wasn't what we were looking for. We're looking for 10x. Any other questions?
Okay, I think we are on time. Okay. So let's thank again, Ron. Thank you very much. Thank you. Now we'll start the closing ceremony. While the general chair comes, I just would like to remember you about the panel, the HPG panel we'll have at SIGGRAPH. Will be on Thursday. All of you are more than welcome to be there, especially the authors. We will have 1 hour and a half presenting a briefing about everything that was shown up in HPG, and also opening for discussion and a panel hope to see all of you there.
Bear with me for just a second as we make the transition, please. Okay, we good? Yes. Okay, thank you very much. It's been a intense 3 days, yeah? Lots of good content. But here we are, we're at the final session. And thank you for sticking around. So we're gonna start with a tribute. As you may know, Steve Parker passed away earlier this year. And Steve was a true titan of the field. This loss is going to be felt professionally by all of us. We owe a certain amount of the lineage of this conference to him and his efforts in the early days of the Interactive Ray Tracing Symposium. Many of us will feel the loss personally as students of his, colleagues, friends. But no one will feel it more than his family. And it's my privilege and honor to welcome some members of the Parker family here with us today. We have his wife, Marianne, daughter, Amber, daughter, Alyssa, her husband, Brian, and Steve's brother, Mike. Thank you. On behalf of the HPG Steering Committee, on behalf of the HPG 2024 Organizing Committee, and indeed on behalf of the entire HPG community, we welcome you. We thank you for joining us in this celebration of Steve and the impact that he had on many of us in the room. So again, thank you for being here. So among Steve's many, many achievements and awards, I think perhaps the most recent is an honorary degree granted by the University of Utah earlier this year. And they put together a video kind of summarizing Steve's career, and I'd like to take a moment and share that with you now. Maybe. Sorry.
Stephen G. Parker has a long list of firsts and bests in the field of computer science. In addition, he's probably the first honorary degree recipient who never graduated from high school.
He grew up in Oklahoma, and he really enjoyed school until he got to middle school when the teachers quit allowing him to work ahead in math. At that point, he became a little bored. He started teaching himself electronics and computers, and unfortunately skipping school. Steve never did get a high school diploma, but he took the ACT test, and based on his outstanding score on that, he was admitted to the University of Oklahoma, where he received a BS degree in electrical engineering. He was drawn to the University of Utah because of its reputation in computer graphics.
I was very fortunate to be able to recruit Steve as a graduate student in my group, and we were a very young group, just starting out, where I had just a few graduate students and a postdoctoral researcher. It was even so early that we didn't have a name for the group, and it was another student, Dave Weinstein, who came up with scientific computing and imaging, which we pronounce SCI. We were the SCI research group, and Steve was one of the inaugural members of that group, and it wasn't long before I learned just how smart he was. I remember giving him some code that I had written to do finite element approximations, and it was probably less than a week that he came in my office and announced that he had made it 7 times faster. And it was just the first of many, many, many times when Steve would do these amazing technical things. There was just a string of impactful ideas that Steve came up with as a graduate student. And then later, after he graduated, he became an assistant professor of computer science here and a faculty member within the SCI Institute, and a number of new innovations and impactful research.
Steve became a world-class researcher and innovator in the category of computer visualization. His research and papers received many awards and acclaim and literally changed the face of computer graphics. In 2005, Steve created the Center for Interactive Ray Tracing and Photorealistic Visualization, which led to a startup company called Rayscale.
Steve Parker founded a company called Rayscale, which was acquired by NVIDIA, which is the largest maker of hardware to support artificial intelligence now and computer graphics. When they bought that company, Steve was required to leave the university and head up a new office that NVIDIA established in Salt Lake City. He's now the vice president of professional graphics for NVIDIA.
Perhaps most of you have never heard of Stephen Parker, but you have no doubt seen his work.
Every time you're watching an animated movie or a special effect in a movie, or you're playing a game, or your children are playing computer games, they're likely going to be utilizing some of Steve's work from either the software or some of the hardware that his ideas have helped to create.
Although no longer on the U faculty, Steve has maintained his affiliation and affection with the U. He and his wife, Mary Ann, have made major donations to support the Scientific Computing and Imaging Institute and the John and Marcia Price Computing and Engineering Building.
And we will be very proud to have their name on one of the most visible parts of that building.
He's both brilliant and he's just a really nice guy.
Steve deserves the honorary doctorate because of the impact that he has had on society and on the university and on everybody who has come in contact with Steve.
In an address given in March 2023 at the 50th anniversary of the Computer Science Department, Steve offered 5 pieces of advice for students.
For the students, I'd also, demand or push it to be a special place. Chase both depth and breadth. Embrace parallelism. Build something ambitious, something that's bigger than yourself. And then finally, respect that you're standing on the shoulders of giants.
One of those giants is him.
I was one of Steve's students, and I just want to share a quick anecdote about the first time I met Steve in person. So this would have been spring of 2002. Gosh, 20 some odd years ago, right? I was a prospective graduate student. I knew actually I wanted to go to the U. I wanted to work with Steve specifically. I had read his I3D paper, and I said, I want to do that. So I looked him up, connected with him, eventually got accepted. But I was out there, as a prospective student, one of these wine and dine kind of things where they bring you in and tell you why it's the right place to be. And Steve and I were sitting in his office. I don't remember the exact course of the conversation, but somehow we were looking at a map of the university campus and some of the surrounding areas there in Salt Lake City, pointing out different things. My then fiance and I, we were going to move across the country from Pennsylvania and both study at the U. So we were just talking about different sites around the city. And I said to Steve, so where do the graduate students live? He, without missing a beat, stood up, walked out of his office. Okay, gonna follow him down the hall. Where does he take me? The grad lab. Now, we all know Steve knew exactly what I meant, right? I was looking for cheap student housing or an apartment or something, where physically or geographically might the graduate students live, but he was right. Over the course of the next 5 years, I undoubtedly spent more time in that grad lab than I did in any of the apartments that I might have occupied there in Salt Lake. So, next up, we have fellow HPG steering committee member, longtime colleague of Steve at NVIDIA, and my current boss at AMD, David McAllister.
That was great. So I first met Steve, I think it was 30 years ago. It may have been 29, back in 1994, 95. He looked like one of those cute young first-year grad students pictures in the video. It was late one night, like 10:30, 11. I was in the undergrad lab, a different lab than the one Christian referred to, and I was hacking away on something. And there was this young guy on the row in front of me working hard on something, and he had a toddler, a 2, 3, 4-year-old little girl playing on the floor, climbing on his lap, just kind of resting on his knees, going back and forth, and he was hugging her and taking care of her. Turns out it was Alyssa, who's right here, and I didn't talk to him that night, but that left a memorable impression on me of how he handled work-life balance and how he handled served his family while still meeting the challenging demands of being a grad student. And let's see. Okay, we'll come back to that one. So to me, that experience illustrates something about Steve that helped him make the contributions that he did. There's this poem by Longfellow, "The heights by great men reached and kept were not attained by sudden flight, but they, while their companions slept, were toiling upward through the night." And that was a literal example of that I saw in Steve that night. And yesterday we got a lot of good breadcrumbs of advice for grad students and the younger generation. And this would be one that I believe in and that Steve exemplified well while balancing life with his family. The one other thing I wanted to note is just a glimpse of one of the several heights that Steve reached, that he attained as a great man, and that was interactive ray tracing. Yesterday in Pete's talk, he referred to the contributions made at the University of Saarbrücken in interactive ray tracing, and Pete glossed over this one. This paper by Steve Parker and several other people who are here today, that was another of the very first interactive ray tracing examples. I was, when Steve had just joined NVIDIA and Bill Daly had just joined NVIDIA, I was there when the two of them met, and Steve said that he had made 6 large ray tracing systems at that point in his career. This was the first. And he said, in addition to many, many one-off experimental ray tracers. So the 6th one of his large ray tracing systems was optics. So he knew a lot at that point about how the ray tracing part of the problem needs to interact with the shading part of the problem and the sampling part of the problem and all the other parts of the problem. And he identified entry points at which one could interface between the shading and the ray tracing. And that's the optics programming model with closest hit shaders, any hit shaders, ray gen shaders, all these terms that 90% of us in this room are now intimately familiar with. That contribution being his 6th deep dive into this problem established the optics programming model, which is, a handful of us, maybe a third of us, have used optics, but many thousands of people have used the optics programming model in DXR and in Vulkan ray tracing, right? So Steve gave us the API, the programming model that's used in approximately all fast ray tracing in the industry today. To wrap up, here's a picture of Steve that I enjoy. Steve liked shiny things. That may have drawn him to ray tracing. Steve liked fast cars. You may remember the SIGGRAPH 2008 demo with, what was the car? Yes, the Veyron, the green, NVIDIA green Veyron demo driving through a city, right? Steve was attracted to fast cars. Here's a picture of Steve with one of his fast cars. You may notice the license plate here. There is, and you're probably wondering if there's a counterpart license plate for completeness, and there is. This is Peter Shirley's car. All right, I'll now turn it back to Christian, who will tell you where we're going with this.
Thanks, Dave. So, in celebration of Steve's personal and professional legacy, his passion for and his commitment to this conference, and for his lasting contributions to the field of computer graphics, the HPG Steering Committee were honored to announce that our annual Test of Time Award will now be the Stephen G. Parker Test of Time Award. At this point, I'd like to welcome our papers chairs to actually announce this year's Test of Time Award.
Thank you. Yeah, so the Test of Time Award, we have tried to figure out which paper that was released 10 years ago during the HPG conference, the High Performance Graphics conference, had the biggest impact. And to do that, we have employed a process where we go to Google Scholar and we look for all the papers that have been released during that particular conference. We count the citations and then we rank them. And then there's one paper that stands out. Can I move this forward? Yeah. So as you can see, the papers from High Performance Graphics had made some impact. And there's one paper that very clearly stands out with no less than 103 citations. And that paper will receive the very first Stephen G. Parker Test of Time Award for this year. And that paper is titled, is that on the next slide? There we go. Coarse Pixel Shading, which is written by a large number of authors, so I'm not going to list all their names. But congratulations, and maybe some applause is in order here.
We do have Aaron LaFawn with us to accept the award. So do you guys want to, it's the top certificate in the mirror. And I'll invite Aaron up here to make a few remarks. Guys, do you want to present the? There as well. Yeah, come on. Sorry, that was less smooth than it should have been. Congratulations, Aaron. Thank you.
Well, I'd like to thank the committee this year and the steering committee and the whole community and my co-authors, which many of them are watching on the live stream, some from Sweden today, all of which wish they could be here. Special, it means a lot to have Steve's family here. You know, this work, which I'll say a bit about in a minute, I think Steve would have liked this one, in that what Steve really focused on in his career. Steve was obviously a groundbreaking researcher, but where Steve's true passion lied was not just in inventing, but taking those inventions all the way to product. It's no accident Steve spent much of his career leading product groups at NVIDIA. And he often would tell me when we'd be talking, he reminded me of this probably at least monthly, that Aaron, the paper, the invention is maybe 10% of the work. There was always another 100x factor Steve was talking about to turn something into a product, and it's quite proud of the fact that this paper did ship in hardware, and this is a predecessor to what is now the modern day variable rate shading that's in Vulkan and D3D. The variable rate shading looks different than this, but this was a step along the way. But with Steve's advice of standing on the shoulders of giants, this work, I think you could look at the origins of this work starting with Kurt Akeley's paper in 1993, where he introduced to us all multi-sample anti-aliasing, of decoupling your visibility rate from your shading rate. Also, Jonathan Reagan Kelly's work in SIGGRAPH 2011, where decoupled shading system was inspiration for this. And then there's a large body of research, that much of it published at HPG before this paper, on stochastic rasterization that inspired this work. Stochastic rasterization was trying to see, can we evolve the rasterizer to shooting many, many rays to accomplish stochastic primary effects? And at this point in time, we realized, as we started this work, that we wanted to see if we could distill out that nugget of this idea of decoupled shading. Can you shade coarser than you are sampling your visibility? And we wanted to see if we could pull that out of this complex body of research that was a stochastic rasterization research into something simple enough that we could put into hardware. And this work was, although he's not an author, he should be, and I'm sure he's the first acknowledgement. But this can't go without recognizing the late Tom Piazza. Tom was a co-inventor of this work. He guided us to go, how do we go from research ideas into something practical, something buildable? Tom was the chief graphics architect at Intel at the time, and was truly a great in our field, and I think an unsung hero. So I'll end it there, and I just, again, want to thank the committee, and it's a tremendous honor to receive this, especially in Steve's name.
Thank you, Aaron. We would be remiss if we didn't also mention the second and third place winners. These will be posted on the website, and so we thank these authors for their contribution, standing the test of time as well. So maybe a round of applause for these folks. Okay, well, I'd just like to thank the Parker family once again for being here, for joining us, for sharing Steve with us these many years, and we just, again, acknowledge the impact that he's had, and thank you for being here. Okay, next up we have the Wolfgang Strasser Best Paper Award, and so once again, I'd like to welcome our papers chairs back to the stand.
Thank you very much, Christian. So we're going to start with the third place best paper, which goes to GPU-friendly stroke expansion by Raf Levien and Armand Ugure. So. Raf, would you like to come up and accept your award? And Armand? On a slightly personal note, I'll admit this was the most fun paper and presentation that I saw at the conference, so thank you.
Appreciate it. Thank you very much.
Thank you. Then for the second place for the Best Paper Award, we have the following paper, HPG, hierarchical parallel locally ordered clustering for bounding volume hierarchy construction by Karsten Bentin, Daniel Meister, Basak, Melhawal, Tsakok, and Kensler. Can you please come forward? Karsten.
Thank you.
Congratulations.
Thank you. Thank you.
Shake your hands. Congratulations. And lastly, the first place winner for the Best Paper Award goes to Real-Time Procedural Generation with GPU Work Graphs by Bastian Kut and several other people, a lot of whom were in this room. So please come up. This was an amazing paper and a great presentation. Congratulations. Yeah, well. No, just accept. Thank you. Now for the Student Competition Award. I guess I will turn this back to Christian.
Okay, moving right along. Student Competition Award, Johannes Meng, one of our program chairs. Again, unfortunately, neither of our student competition chairs could join us here today. So Johannes will be presenting on their behalf.
So first, a few comments, because
there's a surprise. We have a fourth submission. So you may not have noticed this, but we did have some problems with our email servers. And that meant that some submissions got lost, unfortunately. And our student competition chairs scrambled to find out which those were, and I think they found them. And here's the fourth submission that they did find. This is a Stanford Bunny, and let's see, can I? It's a volumetric rendering using single scattering approximations. So this is the four submissions. The competition was judged by Pete Shirley. Thank you for doing this. And I spoke to him before this. He said it was a difficult decision. He liked all of the entries very much. So thank you for doing this. Let's get to the second place. The second place goes to Wenjun Zhou from University of Utah. I believe that Wenjun is not here today, but maybe he's watching on the stream. Wenjun, this is your applause. And we will reach out to you. Now, for the first place. The first place goes to Murilo Mesquita Carolina from the Universidad Federal de Goiás for this fourth submission that we received. I believe Murilo is here today. Are you still here? Would you come up to the stage, please? It's your applause.
Okay, thank you, and congratulations to all of our winners today. Again, a round of applause, please.
Good afternoon. I have just a couple brief messages with two hats. With my sponsor share hat on, I would once again like to thank our sponsors who enabled us to meet in this beautiful venue and enjoy the food over the last several days. Their contributions really make the conference possible. Secondly, as a representative of the HPG Steering Committee, I'd like to recognize the 2024 Organizing Committee. As a lot of people in this room know, putting on a conference with an all-volunteer committee is a lot of work. And everyone on the committee has a more than full-time job, whether they get paid for it or they're hoping for a diploma soon. And it's a lot of work. In particular, though, I would like to thank our General Chair, Christian Gribble, for his hard work. In addition to the extra duties like venue and catering and all of that, one of the key aspects of General Chair, and I've been there, is herding cats and getting everything done and keeping track of everything. And Christian is a real role model of how to achieve that. So let's give him a round of applause.
Thank you, Josh. That's very, very meaningful. I appreciate that a lot. So funny you should mention the committee. I seem to have lost my cursor. We're going to do something a little different this year, and that's a Chairs Award. So I'm a first-time chair of the conference, and I guess it went okay. Hopefully we'll have more feedback in the coming weeks. I'm intending to do a post-conference survey. But in terms of the herding of cats, really, we wouldn't have been able to pull this off without the effort of everybody. But somebody went above and beyond this year, and I wanted to recognize that. And that's our local chair, Kenny. Kenny, are you in the room? Yes, sir. Come on up. So I didn't know Kenny before this little journey we went on together this past year. But But he came highly recommended, and I reached out, I introduced myself. I said, would you be willing to help us out? I'm in Pittsburgh. I don't know Denver. I need help. And he did. He just stepped right in. And Kenny's actually from the scientific visualization community, right? He's graphics adjacent, as I talked about in the town hall yesterday. But he just went all in, and he helped us track down this venue. He helped make all the local arrangements, working with the staff here to make sure everything has gone as smoothly as it has. And that was just a huge weight off of my shoulders, and it was a huge weight off the collective committee's shoulders to be able to get this space and to have you all here and to enjoy the content and the collaboration that's taken place. So again, thank you, Kenny. Thank you so much for your assistance, and I'm glad to call you a colleague. So again, here is your 2024 committee. Let's please give them a round of applause. One of the discussions we'll be having in the coming weeks is what the organizing committee for 2025 looks like. I think I mentioned yesterday you're stuck with me for another year, but there will be some turnover, and we're looking for new ideas and new blood. So please reach out. The email aliases on the web will remain active, coming to this year's committee until we officially turn over. So if you're interested, please do reach out. At this point, though, I would like to welcome Michael Doggett, another member of the HPG Steering Committee, to have a few words about HPG 2025. Michael?
So I'm from Lund University in Sweden, and Lund is about an hour by train to Copenhagen. So there's no one here from Copenhagen, but Jeppe Frisvold from DTU will be one of the chairs of EGSR. And so when HPG runs in Europe, it runs with EGSR. So I'd like to sort of recommend Copenhagen as a great place to visit. It has a very close international airport, which is well connected. And Copenhagen is a beautiful city. In summer, it's very nice. It has a very long history. It's the capital of Denmark. So there's a lot to see. So I'd like to, on behalf of the professors at DTU, welcome you to Copenhagen next year.
Thank you, Michael. I know my kids are already looking forward to this trip. We're planning to hit the LEGO headquarters at some point. Okay, so folks, that's a wrap. That's HPG 2024. Thank you so much. Enjoy SIGGRAPH if you're here all week, and we'll see you in Copenhagen.